Three.js is a JavaScript library that allows you to create 3D scenes directly in the browser, ones that you can actually interact with and put HTML on top of to get to your next page. So how do we go about creating a scene like this? Well, we're going to need to do a few things. The very first is we're going to need to install Three.js, and we're going to be doing so using a front-end framework called Vite. We're going to need to create a scene, a camera, and a render. Three things we'll go over that are part of the Three.js framework. We're going to need to create a plane, and what I mean by plane is a plane geometry. This entire square right here is considered a plane in Three.js, so we're going to need to be able to create that. And then if we look really closely, each individual vertice on this pane, we need to make sure that it moves individually and then interacts with our mouse as we actually move it across the plane. So you'll see right here, we're going to need to add that hover effect I just mentioned. We're also going to need to be able to modify this plane to our taste using something called dat.gui, which is this interface up here. Basically, if I go ahead and start editing this, you'll see the plane in the background begins to edit as well. This is super useful for debugging and making sure that you get the right look on your scene so that your end product looks exactly like you want it to. And then finally, we're going to need to be able to add HTML on top of this and make sure that it integrates with JavaScript so the HTML doesn't get in the way of our hover effect, and then we can go to the next page when we click something like a View Work button. We're going to be covering all of that in this course right here. But I'm also going to be creating a premium course that goes with this as well. This is my portfolio site. It's a very similar effect, a little outdated using an old version of Three.js, but nevertheless, when I click on View the Pieces right here, you'll see that we have this nice little transition that goes and bolts into some stars. We're going to be doing that as a premium course over on chriscourses.com, but everything you see right here that I just went over in the very beginning, we're going to be learning all that right here in this video for completely free. So let's go ahead and begin. To create this project, well, we're going to need a few files. So the first thing I'm going to do is I'm going to open up my Finder window, and I'm going to go to a directory where I'd like to create my Three.js projects. So my home directory right here is Christopher List, simply my name. And if I begin to scroll down, there's going to be a folder in here called 3. This is one that I created specifically for any projects that relate to Three.js. So if you don't have this folder right now, just go ahead and press Command-Shift-N if you're on Mac, and a new window will pop up. You can name this whatever you want. I recommend naming it 3, like I have right here. If you're on Windows, just go ahead and right-click in an empty area and click on Create New Folder, and you should be able to create a folder called 3. So we have this folder called 3. I have another folder inside of it called 3, and that is just for the finished version of this, so ignore that. But we want to create a new folder. This is going to be called my portfolio. So if you see over here, this text, this super edgy text with my name on it and then some sort of description about me, this is an example of a portfolio site. It's about to introduce my work, so people, whether they be clients, whether they be a job opportunity, know what I am capable of in case I would like to pursue a job or a client. So we're making a portfolio site essentially, and this folder is called My Portfolio. My project makes sense. So we have a directory for our project, but now we need to open this up in a text editor of your choice. So the text editor I like using is always going to be Sublime Text. I know a lot of people like using VS Code. No matter which one you use, you should be able to grab this directory and then drag it on top of your text editor, and it should open up directly in your text editor, as you'll see right here. But now we need a few files. We're going to need an index.html file, which basically houses this whole project, and then we're going to need a JavaScript file, which houses all the code for the background scene. So the first thing we want to create is some index.html. If I want to test some HTML in the browser, what I always like doing is just creating a simple h1 tag. And inside of this, just typing whatever text I think of. Hello is the first thing that comes to mind. And if I go to File, Save with this text in here, and you'll see the new tab open. If I go to Save, I can now save this as a specific file. Where do I want to save this? Well, within my 3 directory, and then inside of the My Portfolio directory we just created. So this is going to be called index.html, and make sure you add the .html to the end of this, otherwise the browser won't recognize this as valid HTML, even though we have HTML inside of it. So we're going to go ahead and save this as index.html, and once I do that, you'll see my brackets light up, meaning we have valid HTML inside of here. So we want to make sure we save. I'm going to hit Command S, right click this over in Sublime Text, and then reveal in Finder. That's just going to open up our project exactly where we were. And now what we can do is we can double click index.html, and our HTML is in the browser. So we know our file is being read, which is perfect, but now we need to import Three.js. Well, how do we do that? You'll see over on the Three.js website, their installation page specifically, there are a few ways to install Three.js. One of them is to install from npm, which is package manager, a little more difficult if you're new to JavaScript. And the second is to install from a CDN, and this is basically just copying in a URL that contains the library code and just placing it inside of your project. So you might think that this is probably the easiest way to do it, but let's go ahead and install it this way and see what happens. So we're going to install from a CDN, basically a URL that pulls in all the Three.js code. What I'm going to do is I'm just going to copy these script tags. I'm going to go back over to Sublime Text in our project, and right at the bottom of this, I'm just going to paste in the script tag. So theoretically, we should be able to use all the content within this URL right here. Let's go ahead and see what content is within this URL first. If I go ahead and copy this URL, paste it in the browser, and try visiting it, you're going to see cannot find package 3 at version. That is because Three.js expects you to add a version to this URL before you can actually pull it in. So I'm going to type 0.126.1, which is the latest release as of the time of this recording. And if I hit enter, you'll see this is all the code that Three.js consists of. It's a huge file, but this is everything we need to create 3D scenes in the browser. So we want to make sure we're pulling this into our project. We can copy the URL right here, go back to Sublime Text, and make sure we are replacing this version that just has the version inside of the carriage. We want to go ahead and replace this URL with the one that specifies that we want to use version 126.1. So now on save, if we go back to index.html and refresh, nothing happening. Well, let's go ahead and check out our console. We can check out our console by right-clicking and clicking inspect. If I look inside of our console and refresh, still not getting anything just yet. But if I go on over here to our code and then console log out the scene that we are creating with Three.js and then refresh in our browser, you'll see that we are actually console logging it out. So we successfully imported Three.js. We can actually write all of our code directly here within this script module. Now, typically, I like having all my JavaScript in a separate file because it makes things a little cleaner for when I want to bounce between what's HTML and what is actually JavaScript, what is in the 3D environment. So what we're going to do is we are going to create a new file by going to File, New File. It's going to open up a new file over here in Sublime Text, and this is going to be where all of our JavaScript goes. So we want to make sure that we are saving this as simply index.js. That is going to be our main JavaScript file. So we hit save. We now have a JavaScript file in place. If we go back to index.html, we want to make sure that we are taking this JavaScript code over here, going inside of index.js, pasting it in, and then we need to make sure that we are referencing index.js from our HTML file. So to reference this, we can add in a source attribute, and we want to make sure we're going inside of our My Portfolio directory, which we have right here, and that we are referencing index.js, our JavaScript file. So save, refresh in our browser, and you're going to notice something. We are getting an error. Access to script at this URL from origin null has been blocked by core's policy. Now, cross-origin requests is a whole nother beast. That's probably its own tutorial in itself. But basically what's happening here is since I'm trying to pull in this package directly from a separate index.js file rather than within the script tags from index.html. We're getting this error. We can't actually pull in the scene that we want from Three.js. Now, a quick and easy way to fix this is to set up a local server. Right now, we're simply running the HTML file in the browser, but if we set up a web server, something that's there for the purpose of serving up web files to the browser, this error is going to go away, and you're going to see that shortly. So what is the quickest way to set up a front-end web server? Well, in my opinion, it's using a framework called Vite. Vite is essentially a front-end server created by the same guy who made Vue.js, and whenever you save a file within the server, it's going to automatically update your page with all of your new code, so it's super helpful when you're developing. You don't have to save, go back and refresh. This is going to refresh everything automatically. So this is what we're going to be using for our server to make sure we don't get that weird CORS error whenever we are importing Three.js. So how do we install Vite? Well, we're going to open up a new tab, and we're going to visit vite.js.dev. We're going to click the Get Started button, and we're going to start scrolling down, And right here where it says scaffolding your first vite project, this is what's going to help us create a vite project. So we want to use what is called npm, Node Package Manager. If you're unfamiliar with it, basically it's a Node.js app that allows you to download external packages from other authors, such as Three.js, Vite, Vue.js. You can install all of those using npm. And the useful thing about downloading packages with npm is you're always going to have a list of all the packages that you're using within your project and what versions they are, so that if another developer were to come in and use your project, they'll know exactly what the project is using. So two things here. One is Vite requires Node.js version 12 or over. And two, we need to make sure that we run this directly within our terminal with npm. So you also need npm installed. Well, what happens if I don't have either of those? If you don't have Node or npm, or your Node version is under 12, what you want to do is just type in Node.js. The very first result is going to be the Node.js official website. You can go ahead and click the download option right here. And then you want to find the installer of your choice, whether or not you're on Windows or Mac. I'm on Mac, so I would click this one. And it's just going to download this package that will allow me to install Node.js, specifically version 14.16. You'll see if I were to go through this whole thing, I would install that version directly. I already have it installed, so I'm not going to go through. But if you don't have it installed, make sure you are installing it with the Windows or Mac installer. And once you get through all of those prompts, you should have Node.js installed in your system, the correct version, because this is version 14.16 as of this date. And also, whenever you install Node.js, you also by default install npm. So npm should work for you by default as soon as you install Node.js as well. So once you have Node installed, let's also install Vite, because we now have npm as well. So to run this command, we're going to need to open up a terminal window. Well, how do we open up terminal on Mac? We're just going to click this little magnifying glass right here, spotlight search, and type in terminal. And you're going to see we get the terminal result. We're going to click it, and it's going to open up a new window. This is the project currently running in the background, so I can show you guys, but for you guys, it should open up a new window, and yours is going to look white. Mine only looks black because I have a little bit of customization put in here. It's going to start you off directly on the home directory right here, which is a little squiggly. But before I continue, for you Windows users out there, you're not going to be opening up terminal, you're going to be opening up something called PowerShell. It's basically the Windows equivalent to what we have right here, and it's pretty easy to navigate for the most part. Maybe not as nice in my opinion, but it'll still get you going where you need to go, and you should be able to input these commands as well. So we're starting off at our home directory, which is notified by the squiggly, and if I ls, which means to list the contents of this directory, you'll notice our home directory is 1-to-1 with our home directory over here in the Finder. If I start scrolling down to the visible folders, you'll see all of these match up with what we have in the terminal, which is pretty cool. So we want to make sure in the terminal that we're going inside of the current project we're working on. So let's do this the easy way by finding it in Finder first. We're going to scroll down to 3, and inside of here is our My Portfolio project. So if I want to go to this directory directly within my terminal, what I can do is type in cd, which stands for change directory, and I want to change directory into My Portfolio. So I'm just going to grab this directly from Finder, drop it into the terminal, and it's going to give me the exact pathing I need to go to in order to dive into this within terminal. So if I cd directly into this and hit enter, you'll now see we are inside of My Portfolio. We can list out the results of this folder, and you'll see we have index.html, index.js. This is perfect. This is exactly where we want to run npm init vite.js/app. So we're going to go ahead and copy this, and remember, make sure you have a Node version over 12 and that you have npm installed, which comes with Node, so just make sure you have Node. We're going to run this command and hit enter. So what is the name of our project? Well, it's not Vite project, it's going to be My Portfolio. It's going to give you a little prompt that we need to select. What kind of JavaScript do we want to use? Do we want to use any template associated with this Vite project? Well, for our purposes, we want to focus on just Three.js. We don't need any of this other stuff right now, so we're going to select vanilla, which is just basic JavaScript, and that's all we need to do. So if I go back to Finder, we're going to see what that command just did. We don't see anything here just yet, but if I click My Portfolio, well, we just scaffolded a whole new directory called My Portfolio. And inside of here are going to be a few files that Vite just created for us so we can set up that front-end web server. So we have two instances of My Portfolio, but really we want to use the one that we just created. So what I'm going to do is our initial My Portfolio, I'm going to call it -old. I'm going to drag the new vite my portfolio into our root 3 directory. And then I want to make sure that I am cding inside of that vite my portfolio. So here in terminal, I can type in cd, just drag my folder on over here, hit enter. And now I'm just going to follow the commands that we see right here outputted by vite, specifically these bottom two, npm install and npm run dev. So if I copy these and paste, hit enter, we're going to see a few commands taking place. npm install, what does that do? Well, if we go ahead and open up my portfolio in Sublime Text, which you might need to do again since this is a new vite project, if I look inside of package.json, npm install is going to install all the dependencies listed out within this file and their specific versions. So npm install just installed vite version 2.1.0 because it is listed out as a dev dependency within this file. And then when I run npm run dev, well, it's telling terminal to run this command right here. So we're running a vite command. It's basically just an alias or another word that says run this command. So all we're doing when we run npm install is installing vite, and then we are running it when we run npm run dev, which you see right here. So when those commands run, you're going to see that we are now presented with a vite dev server is running at localhost 3001 for my instance. For you, it's probably 3000. I just have another server running in the background. But now what we can do is if we go back to our project, you'll see here, we're just opening up the file in the browser. If I go ahead and open up a new tab and then paste in localhost 3001, which was presented to us over here, and hit enter, well, we now have a vite app in place. And like I said, the very cool thing about vite is if we go ahead and start editing some of the contents within our project now, such as going into main.js, you'll see that this is where we are rendering out hello vite in the documentation on the page. If I begin editing this to something else, edit, and hit save, watch what happens. No manual refresh required, everything is just instant, so it's going to be very helpful for when we are working with on this Three.js project. So let's get back to the focus of Three.js, get all this weird server npm stuff out of the way for the time being. If we go back to Finder and open up our old My Portfolio project in Sublime Text again, go back to index.html, you'll see that we were importing index.js, which just wasn't working for us before. But if I go ahead and copy the contents of this, and paste them into our vite app, we can get rid of everything that we see right here. And then I hit save and open up my console in the browser. You'll see that our scene is now showing as expected once more. So now we can have a separate JavaScript file that loads Three.js without that CORS issue taking place. So now if we go back to our to-do, we can go ahead and check off install Three.js using vite. Perfect. So the very next thing we want to do is create a scene. We want to create a camera, and then we also want to create a renderer. These are all things that are required to get to some sort of interface on the screen. So we already have a scene in place. If you look right here with the default boilerplate code provided by Three.js, we are creating a new 3 scene, and we are storing it inside of a scene constant. So we created one of the 3 things that we need. We have a scene, but now we also need to create a camera. So to create a camera, I'm going to create a constant called camera, and this is going to be equal to a new 3 perspective camera. And a perspective camera takes 4 arguments. The very first one is going to be the field of view, which is a value in degrees. So it's kind of like whether or not you would like your camera to be a wide angle lens, which shows a lot of the scene altogether, or whether or not you'd like it to be a telephoto lens, which only shows a small portion of the screen. So the degrees we want to put in here for our field of view is going to be 75. That should show a ample amount of screen. This is the default Three.js usually uses. So we're just going to go with that. The second argument for perspective camera is going to be the aspect ratio of our scene. So if we look back at our initial project, you'll see that our scene takes up the entire width and the entire height of our browser window. So the aspect ratio that I want is going to be our window's inner width divided by our window's inner height, and that is going to give us the exact ratio we need so that when this camera is looking for objects on the scene, it's going to know to size them to the correct dimensions relative to our browser window, specifically its inner width and its inner height. The next 2 arguments are going to be clipping planes. What is a clipping plane? Well, a near clipping plane, which is the 3rd argument, is going to state how close does an object need to be to the camera before it actually gets clipped out of the scene altogether. Clipped out of the scene just means it doesn't show on the scene. This is all going to make a lot more sense as we go through it. These two aren't that important to explain right now. So for the near clipping plane, we're going to be putting 0.1, and for the far clipping plane, we're going to be putting 1000, so we can see all the objects from a distance of 0.1 from the camera, very close, all the way down to 1000 units out there in our scene in 3 dimensions. Anything past 1000, we're not going to be able to see. So we have our camera, but what do we need next? Well, now we need a render, something to combine the scene and camera together to put something in 3 dimensions on the screen. So to create a render, we're going to create a new constant called render, and this is going to be equal to a new Three.web.gl renderer object. And now, just to make sure that these are all instantiated correctly, what we can do is we can console log each one out individually. So we already have our scene. We'll go ahead and console log out our camera as well. We'll console log out our render too, and we don't even have to refresh because Vite does it for us automatically, and you'll see each of these was created successfully because we see their individual objects being outputted in the console. If you're not seeing this over here in the console right now, just double check your code and syntax to make sure you have 4 arguments within a perspective camera object and that you are typing out WebGL render correctly over here when you create the renderer. So we have these 3 objects, but we're not seeing anything on the screen just yet because all we're doing is storing these within constants. We actually need to make use of them now. So our renderer is basically a canvas HTML element that runs WebGL, which is basically the framework that's required to run 3D on the web. So what we need to do is we need to put this canvas object directly within our HTML, and to do that we're going to be using JavaScript. We're going to be injecting it into our HTML. So to inject it into our HTML, we can select our document object, specifically our body, which if we look in our elements tab over here, we're going to be injecting it directly within this body tag. We want to append a child element. What child element do we want to append? Well, our renders DOM element. And just by doing that, you'll see over here we now have a black box, and this is what's going to be representing our scene where we can edit 3D objects. If I go ahead and inspect this, you'll see we just appended in a canvas object, and this canvas object is what's going to be running WebGL, which allows us to run 3D stuff in the browser. So cool. Now, one issue we have here is obviously this canvas element isn't the full width and height of the browser. So what we can do is, before we append our renderer's DOM element, we can go ahead and select a renderer and use a set size function to say what size should our renderer element actually be before we append it onto the browser. Well, the first argument here is going to be the width we want this element to be. So what width do we want? We want the Windows inner width. And if you're wondering where this variable is coming from, well, this is the exact same thing as window.innerWidth. The thing is, whenever you're referencing the window object within your code, you don't actually need the window object. If you reference a property directly from the window object, it's going to know what you're talking about automatically. So therefore, we can use inner width and inner height by themselves. It just makes our code a little cleaner. So our width is going to be equal to the inner width of our browser, and then our height is going to be equal to the inner height of our browser, the full width and height. So now if I save, you'll see now it's taking up pretty much the full width and height, but we still have some padding up here. Where's this padding coming from? If I go ahead and inspect our page and look at our body element, you're going to notice by default, it has a margin of 8 pixels. Every website you create, the browser is automatically going to be adding on 8 pixels to the margin of your body element if you don't specify otherwise. So we don't want this margin there at all. What we can do is go to index.html, and within our head tags, we're going to be creating a style tag, and this is where we can add some CSS to take away this default margin. So what I can do is I can select our body element by typing in body, and then what CSS do I want to alter? Well, simply its margin. And instead of 8 pixels, I want this to be equal to 0. We don't want any margin at all. So if I save this, we get an auto refresh and that margin goes away. And now I can't really scroll to the left or right. There are no scroll bars in place, which means that our Three.js canvas is indeed taking up the full width and height of the browser. So that will take care of that. So if we go back to our to-do list, we created a scene, we created a camera, and a render. And now we actually put our renderer on the screen, and this is going to be acting as a canvas in which we inject 3D objects onto this, and we can interact with them in a 3D space. So technically we can go ahead and check off create a scene, camera, and render from our to-do list, but now we need to actually get some sort of geometry, some sort of mesh within this screen so we can start interacting with it. So the very next step we're going to do is create a plane. But to make this as easy on you guys as possible, I'm going to start with the most basic object, which is actually going to be a box. So whenever you want to put some sort of element within your Three.js scene, you're going to need two things. One is going to be you need a geometry. A geometry is basically the wireframe of your object. It contains data relating to all of that object's vertices, which actually start piecing together the object, such as a box. So we'll have a vertice here, 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 has data related to all those vertices that connects them into a box shape. The second thing we need is a material. The material is what goes on top of this geometry to actually fill in everything in between. Vertices are just points that really create some sort of wireframe, but to fill in that wireframe, we need some sort of material in place, which is basically just painting up the faces of the box. So if you have a geometry and you have a material, together you can create a mesh, which you can then put into your Three.js scene and it'll render correctly, which you'll see very shortly. So to create a box geometry, what we're going to do is we're going to create a new constant. We're just going to call this box geometry. Makes sense. This is going to be equal to a new 3.boxGeometry. And make sure your casing is correct over here. So this takes 3 arguments specifically for the box geometry. Three.js has a lot of different geometries that you can go ahead and use within your project. Box geometry is just the most simple one to start with. If you'd like the full list of which ones you can use, you can simply head over to the Three.js docs, and there it'll give you a comprehensive list of all the geometries you can actually use. But let's focus on box geometry. What arguments does a box geometry take? Well, it takes a width, it takes a length, and then it takes a height. So the 3 things we actually need to build a box in 3D space. So the width of our box we're going to declare as 1 unit. You can kind of think of this as feet. I'm not sure what the exact units are actually within Three.js, but we'll go ahead and say that this is going to be 1 foot for the width, 1 foot for the length, and then we're going to use 1 foot for the height. So if I save this and then console log this out just to make sure that we instantiated this correctly, go over to our console, you're going to see now we have a box geometry object. And if I look inside of this, specifically within this attributes property, well, inside of here is going to be all the data related to our vertices, everything that is actually required to get this on our screen. Why are we still not seeing anything even with all this data related to a box and its vertices? Well, simply because we don't see anything until we create a mesh, which remember requires a geometry object and also requires a material object. So that's going to be the second thing we create, is a material object. So we'll go ahead and say const material is equal to a new 3.mesh basic material. And this takes an argument of an object, and inside of this object we can specify a color, and this color is in hexadecimal value. So if I want to go ahead and create a color of green to start, that's pretty basic. What I'll do is I'll type a 0x to declare we want a hexadecimal value in here, and then I can write out that exact hexadecimal. So 00 means our red value is going to be 0 out of 255 if you're used to using RGB values. The second 2 numbers here are going to declare how green should this object be. If I want these to be as green as possible, well, we don't want to use 0. We want to go all the way up the hexadecimal scale from 0 to 9 to A to F, which is going to be the brightest version of that color. So our green value here is set to the brightest color it can be. And then our blue value, which is the last 2 numbers, is going to be nothing at all. And if you don't want any value there for that kind of color, you just add in 0, 0. So we save. It's going to refresh for us automatically. But now we want to console log out our material. And it looks like our material was created successfully. So now that we have a geometry, we also have a material. We can use the 2 in tandem together to create a mesh. So I'll create a constant called mesh. And this is going to be equal to a new 3 mesh. And what arguments does a 3 mesh take? Well, simply a geometry and then a material. So we want to make sure we're using box geometry here. Our material is already called material, and if we console log out mesh, now we have a mesh successfully created. So looking in good shape, but how do we finally get this mesh into our render? Well, we want to take our scene object and then call its add function. This is what's going to add meshes into our scene. What mesh do we want to add? Well, the box mesh that we just created. Now, still not seeing anything even when adding the mesh to our scene. And that is simply because although we put our render within our HTML over in the browser, we're not actually calling any render function, which is going to render out our scene. And to actually render out all the objects on our scene, well, we need to call our renderer and call its render function, which takes two things. It's going to be the scene we want to render out, and then the camera we want to use to be able to actually navigate and move around in our scene. You'll notice we didn't actually use camera anywhere just yet. This is where it's going to come in handy to actually display what we want to show directly within the scene. So if we go ahead and select our camera constant, copy it, and then paste it into this render function down here, it's being called off of our render, and hit save. Still not seeing anything. I know it's probably getting frustrating at this point, but it's there now, I promise. How do we actually see the box that we just created? Well, we want to select our camera, and we want to select its position property, specifically where it is on the z-axis, so going forward or backwards. And we want to make sure that it's not located in the center, because everything by default is going to be spawned in the center unless you specify otherwise. So we're basically going to be moving our camera from the center of the screen, where a box is also spawned. We're going to be moving it backwards so we can actually see what's right in front of it. So if we set it equal to 5 feet, 5 units within Three.js, and hit save, finally going to see our box, although it kind of just looks like a square at the moment. To start seeing this in 3D, what I want to do is add in some animation. So to create animation, we're going to be doing exactly what we do within our Canvas games if you've ever watched any of those tutorials. We're going to be creating a function called animate, and inside of here we're going to be calling Windows request animation frame function, which in return calls another function. So what we're doing here is, if we were to call animate, it's going to run request animation frame, which in return calls an animate function, which is declared right here, which just means it's going to run the code again. And it's basically just going to put us into this loop specifically so we can start animating values as we need to as we begin coding our project. But in order to activate this animate function, at the very bottom, we need to actually call it so it begins the loop. So if I call animate, not going to see anything just yet, but if we go ahead and put render inside of this animate loop, so we're calling render over and over and over again, and select our mesh, specifically its rotation, start with the x-axis, and start adding on 1 over time as animate begins to call itself. We hit save. You're going to see that it's spinning very, very quickly along the x-axis, so it's probably spinning, I believe, forwards at the moment. Let's go ahead and slow this down. Instead of increasing by 1, we're going to increase by 0.01. And you'll see that spins a lot more smoothly. Let's go ahead and add on some rotation to our y-axis as well. And now you'll see the full 3D object in here as a cube as it begins to spin. So right off the bat, when we're looking at this, you'll know it's a little jagged on the edges. If it's looking jagged for you guys as well, it's probably due to the device monitor you're using. So right now, I'm on a MacBook Pro, which has a Retina display, and when I try rendering out this WebGL by default, it creates a little bit of jaggedness along with the actual rendering. To fix this, where we have our renderer created, and where we are setting its size, right after we set the size, what we can do is select our renderer and call set pixel ratio. And this is going to be equal to our window object, which we don't need to actually specify. It's going to be equal to our device's pixel ratio, device pixel ratio. So if I go ahead and save this, it's going to refresh automatically, and you're going to see the jaggedness is reduced significantly because we're telling Three.js what the ratio of pixels are on our device from width and height, and it's going to make sure that it renders things clearly just because it knows that additional data. So we have a simple box on the screen, but if we go back to our piece over here, we don't want a box, we actually need a plane, just a nice flat square or rectangle. So how do we go about putting a plane within our project rather than just this simple box? Well, let's go ahead and focus over here. The first thing I'm going to do is start deleting out our console logs so we can go ahead and focus on the code at hand. So I'll delete these ones, and these ones, since everything is working, we know that. And we don't really need those additional consoles right now. So a new mesh, even if it's a plain mesh, requires two things. Well, it's going to be a geometry and a material. But this is just going to be a different kind of geometry. So you might be thinking, can't we just copy line 18? And instead of box geometry, can't we call this just plain geometry? And then set it equal to a plain geometry object. Well, yes, technically this is how we are going to be doing things, but what we don't know here is what arguments does a plane geometry object take. So if you don't know what arguments a certain geometry or material takes, the best thing to do is go to the docs. So I'm going to show you guys how to use the docs within Three.js to create this plane piece for when you're creating new objects yourself. So what you want to do is open up a new window, and you're just going to type in Three.js docs. Go ahead and full screen this. We're going to click the very first result. This is on Three.js.org, and then we can go ahead and start scrolling down on the left hand side to see what is actually available to us. So when you're looking for what geometry you want to use, what kind of shape do you want to create, you want to scroll down to the geometry section. You'll see right here we have an option for box geometry, which we just used. We just created a box, but we used a more simple material than what you're seeing right here. You'll see this code looks exactly the same to what we just put in, or at least close to the same. But we want to use a plane geometry. So we'll go ahead and scroll down. We see plane geometry is here underneath the geometry section. We'll click it, scroll down. This is what a plane looks like. This is indeed what we want to create that background effect. And now we can look at the code example to see how this is made. So it looks like it takes 3 arguments. Well, what do these 3 arguments actually mean? If we go down to the constructor, we can see what they mean exactly. The first argument right here is the width. This is equal to a float data type. A float data type is just a decimal number, basically. What is the second argument it takes? Well, it takes a height, also a float, a decimal, and then it takes width segments and height segments. So how many segments should be put in between the full width and height of the plane? You'll see right here, it looks like we have 2. So let's go ahead and create our own plane geometry using this plane geometry constructor example. So we know that we need to put in a width. Let's go ahead and start with a width of 5 units. We'll also start with a height of 5 units as well. So we have a perfect square here. Width segments, it doesn't really matter what we put here since we're not using any segments just yet. We'll go ahead and start with 10. And we'll also specify our height segments, which is an integer, so a whole number should also be 10. We have our plane geometry. We can go ahead and console log it out to make sure that it was created successfully. Go back to our project, refresh, and it looks like indeed it was created successfully. So now we need some sort of material in place. We can just go ahead and use the same material that we created for our box geometry, but we're actually going to assign it a different color just so things don't blend together as we begin to test this. So I put this beneath plane geometry. I'm going to call this plane material. And then I'm going to specify our color for this should be red instead of green. So I'll get rid of the brightness values on the green value over here. Put those to 0, 0. The first 2 numbers here are going to be the brightness values for red. If I turn those up to F, which is the brightest value, we're going to have a red plane material. And whenever we have a geometry and material ready to go, well, we can go ahead and call this new 3 mesh code. So we want to create a new 3 mesh that uses our plane geometry, and that also uses our plane material. And we want to set this equal to our plane mesh. And whenever you have a mesh ready to go, all you need to do is add it to the scene with scene add plane mesh. And now you'll see our plane mesh was added to the scene successfully. And if you actually want to see this move in 3D, what you can do is you can select your mesh within your animate loop, so plane mesh, and start adding on to one of its values, such as rotation.x, add on 0.01. And you'll see now our plane is flipping, albeit very fast. That's a little better. Both of these spawned right in the center, so you can kind of get an idea of where these are located and what they look like as things begin to flip. Now, you'll notice as our plane begins to rotate, well, the other side of it just isn't visible at all. And this is by intention by the Three.js authors. They want to make sure your scene is as performant as possible. So when you get to the other side of a plane, it's just not visible by default, but we can make sure that it is by declaring a property within our plane material. So we declared its color, but we can also declare a side property and set it equal to a 3 dot double side. Both D and S should be uppercase here. And if we do this, you'll see both sides of the plane are now visible. This is probably what we want to stick with while we develop, just so we don't get confused as we begin to move around our scene, whether we go under the plane or over the plane. We want to make sure that we can see both things here. So we have our plane in place. This box geometry isn't really serving a purpose anymore, and now that we kind of got our hands wet with geometry and materials, so what I'm going to do is I'm going to remove it from the scene altogether. We can just go ahead and delete the box geometry, the material, the mesh, and then the scene.add where we actually add the box mesh. And then we also want to make sure that we are deleting the mesh rotation down here, which is forcing it to turn and twist in those directions. So if I remove all of those, now we just have our plane. We don't want our plane continuously rotating like we see right now, so I'm just going to go ahead and comment out this code. And now we basically just have a square that doesn't really have any dimension associated with it. So one thing we can do here is we can begin giving this a new type of material, one that actually interacts with light, so that when we begin moving the segments of our square in different directions, we're going to be able to see all the little segments associated with our plane. Right now they're all flat, we can't see anything, especially because we're using the mesh basic material object, which doesn't react to light. So if I want this to be able to react to light, I'm going to use a new type of material. Specifically, I'm going to use a mesh Phong material. And this can take the same arguments that we have within our mesh basic material. If I save this, we're just getting pitch black compared to the red we saw before. This is because in order to view this material, mesh Phong material, we need to make sure that we have a light on the scene, something to actually illuminate it. So the next thing we need to add to our project, our scene, is going to be a light. So let's go ahead and do that now. If I create a constant called light and set it equal to a new 3 directional light. This is going to take two arguments. One, the color of the light, and two, the intensity of the light. So for the color of our light, we can specify a hexadecimal value, which remember we do by declaring a 0x. Going to make sure it's in that hexadecimal format. And then what is the actual color and hexadecimal value? Well, I just want this light to be a pure white. So I'm going to make sure that we add in 6 Fs to declare RGB. Should all be as bright as possible, which when combined creates a white color. The second argument here is going to be the intensity of this light. I want it to be as bright as possible, or at least as bright as Three.js allows, so I'm going to be setting it to 1. And not seeing anything yet, because remember, whenever we create a 3 object, we need to make sure that we position it correctly, and that we actually add it to our scene so that it's rendered with everything else. So to position this, I'm going to select our light constant, select its position, and then I'm going to call a quick set function. So what does this set function take? Well, it takes 3 arguments, x, y, and z. Where do we want to put this relative to the center of where it is placed right now, the center of our scene? So I don't want to move it left or right, so I'm going to select 0 for the x. I don't want to move it up or down, at least not yet, so I'm going to put 0 for that as well. But I do know I want to move it towards me, because if I look right in front of me, that is where the plane is actually placed by default. So if I move that light back from our plane, basically putting the light right in front of it by putting its z value to 1, and then I add the light to our scene, you're going to see we have our light shining directly on our plane. This looks a little different than our mesh material. You'll see right here, we have a little bit of different color taking place here compared to everything just being the same value of red. It's a little lighter in the middle than it is on the edges of our plane, which is perfect for when we need to start editing the vertices to create that jagged-like effect we see over here within the example. So in order to add the jaggedness, we're going to want to be dealing with our plane mesh object. So what I'm going to do here is I'm going to console log out our plane mesh and see what's inside of it. If I console log this out, I can open up our mesh object and start looking around at all the properties that a mesh actually consists of. We're going to want to focus on our geometry object, which is actually the plane geometry that we created earlier. But this is what we're going to be editing to make sure that we get that mountain-like jagged effect. Inside of our attributes property within the geometry property, we're going to have another property called position. And this position property contains all the data related to each of our vertices within this plane geometry, specifically within this array. So if I go ahead and open up this array, let's focus on the first 3 values with an index of 0, 1, and 2. So these guys right here. These 3 values, when used together, represent one vertice within our plane. So if I look at the value negative 2.5, that is going to be the value for this vertice's x position. So where is this vertice of the plane on the x-axis from left to right? Well, negative 2.5 is probably going to be somewhere along the left-hand edge of the actual plane. The second value right here, 2.5, is going to be the y-coordinate of the vertice. So where is 2.5? Well, it's going to be somewhere up here along the top of our plane. And finally, this last one of the trio is going to represent the z value of this vertex, which is going to be 0 because our plane doesn't actually have any depth. If we look at the third value For every single index in here, it's always going to be 0 simply because a plane has no depth. It's saying that the vertex's position on the z-axis should be equal to 0 within our scene space. So our vertices are stored in this group of 3 format specifically because it is better for performance when running them within the browser. It does make things a little harder to edit since we want to make sure we're editing these values to alter our vertices, move them around a bit, but to preserve performance, this is better than putting these in their own individual properties such as an X position, a Y position, and a Z position. It just wouldn't be as efficient otherwise. So basically what we need to do here is to create some sort of jagged effect, we need to start editing each individual vertice's positions within this array. So the very first thing we're going to do is we're going to select this specific array. So we're console logging out our plane mesh, starting right here. If we start diving into this, we want to get our geometry, so .geometry, and then we want to get the attributes. So we'll go ahead and select attributes like so. We'll go ahead and go in a little deeper. We want to select our position, the position of each individual vertice within this plane, and then we want to go into our array, which has all the values where our vertices are located. So .array. If I save this, we get that array specifically. And now we can begin editing the values inside of it to affect our piece over here. So to edit these values in groups of 3, I'm going to use a for loop. I'm going to declare a let called I, set it equal to 0, and then I'm going to specify how many times do I want to loop through this. Well, I want to loop through this for as many items we have within this array over here, which is 363. So if I go ahead and replace array length with our array and then call length on top of that array, we're basically saying we want to go through this for loop 363 times. Now, just looking at our for loop right now, this is kind of messy just because this value right here is so long. It makes our for loop a little hard to read. So something that we can do is we can take this, cut it out of there, cut it out of our for loop, and we're going to create a constant, and we're going to use 2 curly brackets, one opening, one closing, and put inside of here array. And what we're going to do is set it equal to that value that we just cut, paste it out right here, and we are going to delete the last portion of this .array.length. So this is called object destructuring. What we're doing is we are still selecting the position attribute of our geometry object, but we are creating a new constant called array that references that position attribute's array directly. So this right here is essentially getting transferred to this small constant over here, and by doing that, we can use the small constant within our for loop and reference its length like so. So we're still getting the length of our position array, we're just doing it in a cleaner manner within our for loop by using a little bit of object destructuring. So this should still loop 363 times. If I go ahead and console log out I, you'll see that we are still going through this 363 times. We're just not seeing 363 because this counts as 0 as 1. But this is working exactly like we would like it to. So if we start console logging out our array values, which we are going to access using this let we declared up here, we can select our array and say we want to console log out each value within it by placing I inside of here. You'll see all those are outputted into the console. So these first 3 values are related to one vertice. Let's say we only want to loop through the vertices, each little individual vertice related to our plane, rather than each of the values associated with that vertice, such as X, Y, Z. We don't want to loop through all of that, but just each individual vertice, so these 3 together. What we can do is instead of adding 1 onto I, we can add on 3 instead. So now we're only looping through every 3 values compared to every value within this array. And to make this a little easier to understand, we can start setting these values equal to their X, Y, Z counterparts using constants. So I'm going to create a constant called X, and that's going to be the very first value within our array. Very first value within our array is going to be equal to 0, which is what I is equal to. So X technically should be equal to negative 2.5. Then I'm going to create a constant called Y. This is going to be equal to the second value within the array. So when I is equal to 0, we know we get the first value, but if we add 1 onto I, well, we're going to get the second value, which is going to be equal to 2.5. And then finally, we have our Z, which is going to be the third value within the array. That is going to be equal to 0. And once we run through this first iteration, well, we're going to be adding 3 onto I. So if I, let's just say hypothetically, is equal to 3, well now, if we put 3 inside of here, we're going to be selecting the fourth option within our array, which is going to be negative 0.2. we add 1 onto 3, that is going to be 4, so we're getting 2.5. And then finally, if we add 2 onto 3, well, that is going to be index number 5. So if we count 0, 1, 2, 3, 4, 5, we're going to get 0 for that. So this combination of XYZ right here is going to be equal to the XYZ position of each individual vertice. So using these XYZ positions, what we can do is we can start altering these positions to start randomizing the geometry of our plane. So if I want to begin editing the X position of each of these individual vertices, what I want to do is I want to select our actual X position, which is going to be referenced from this array with a value of I, not X exactly, because this is going to be a new value that doesn't actually alter the original. We want to make sure that we are setting array I equal to array I or X. Here we're going to be using X because it makes a little more sense logic-wise. And we want to add on some sort of value. So let's say we want to move all the X vertices to the right by something like 3 units. You're going to see pretty much everything was moved to the right, except for the very first vertice over here. Now, why wasn't that vertice moved? Well, simply because while I was explaining this, we changed I to 3, which means when we're editing the vertices in this loop, we're skipping over the indices 0, 1, 2, which is going to be that very first vertex. We want to make sure we set I to 0, so we make sure we select it, and now everything was translated to the right. If we want to make sure that we're translating it to the left, we can just go ahead and subtract 3. Now everything on the X is moved by 3. But we want each individual vertice to have some sort of randomness associated with it, especially on the Z-axis, because on the Z-axis, that's what's going to make things really bulge out within the shape that we have right here. So let's go ahead and start with Z. To go ahead and set the Z position of one of our vertices, we're going to go ahead and add 2 onto I right here, because that is going to give us the third data value within our array. And we don't want to use the current X position, we want to use the current Z position and start altering its value. So if we go ahead and add 3 onto Z, it's just going to look a little bigger because we're moving it closer towards us. But what if we add a randomized value here? Instead of 3, what if I go ahead and add on math.random? Any value 0 to 1. Well, things are starting to look pretty crazy here once we save that. But we can't really see any of the depth of the inner vertices. You'll see that it's just still all flat. Well, why is that? By default, that is just the way a mesh Phong material interacts with light. So if we want to see all the little individual faces within this plane using a mesh Phong material, what we can do is we can add on a flat shading property and set it equal to a 3. Make sure that's all uppercase, flat shading property. And if I save this, you'll see that our plane is basically magically transformed into this nice geometrical object. So going back to our loop, if I comment this out, you're going to see we still get a flat plane, but when we start altering all the Z coordinates, and we have this flat shading turned on, we can see all the depth associated with those Z position translations. So now, when we go back to our to-do list, we can successfully check off creating a plane. This is great for the basics. Obviously, we're not completely there just yet, but we're moving in the right direction. So the next thing I want to do is be able to modify this plane to the exact dimensions that we would like until we get something that we're happy with. Now, in our code, we could do this simply by changing the dimensions within our plane geometry instantiation. So here, we can go ahead and change the width to something like 10, the height to something like 10, save, and refresh, and you're going to see it is quite bigger. And we can keep toying with these values until we get something that we like. The only issue with this is it's kind of slow. We're going to have to keep going back and forth, changing values over and over again, and it's just not as efficient as it could be if we were to use something called dat.gui. So if we look at the example, this little control panel right here is known as dat.gui. It's a graphical user interface to change different things within your screen. Here I've set it up to manage a few properties: the width of our plane, the length of our plane, how many segments are within this plane, both on the width and height section, and then I believe this controls the hover color. Yes, it looks like it does. I can turn this down, it changes to a different color when we hover over it. So you'll see dat.gui makes this really easy to edit and get to the exact dimensions that we would like to use within our actual piece, rather than having to play around with all these different values by hand within our code. So how do we begin using dat.gui within main.js? Well, one way to do it is you could go inside index.html and pull it in through a CDN link within a script tags source attribute. But if we want to do things a little more professionally, we'll actually install dat.gui through npm, similar to what we did with vite. So to install dat.gui into our project using npm, we can open up our terminal again. I'm going to open up a new terminal tab, and you'll see inside of here I'm already within our project directory. You'll see this is indeed our vite my portfolio project, and here is where I want to run npm install, and then the package name we want to install, which is going to be dat.gui, GUI. And then I want to put -- save at the end of that, and when I put the -- save at the end and hit enter, you're going to notice inside of package.json, dat.gui is now listed out as a dependency. So we can say our project depends on this one library to work. Technically, this could be listed as a dev dependency because it's something that will probably only show in development anyways. But for this instance, it doesn't really matter where you put it, whether it be dev dependency or dependency. We just want to make sure that it's in our project and downloaded. So after installing dat.gui, now you can use it within your project. So if I go over to main.js, I can scroll to the very top of this, and similar to what we did with Three.js, installing that into our project so we can use it, we are going to import the whole library of dat.gui as dat from, and then what is the package name? Well, if we look within package.json, the package name is dat.gui. So we can copy this, go back to main.js, and say we want to import dat from dat.gui. We can test this by console logging out dat, going back to our vite app, and if I refresh, you're going to see we have a module here. If I open it, well, it looks like we have some GUI functions and methods inside of here, so we successfully imported dat.gui using npm, so we're on the right path here. So to start using dat.gui, we need to start adding in little individual property sections to start altering everything within our app. So the very first thing I'm going to do is I'm going to create a GUI object. I'm basically going to instantiate dat.gui. So I'm going to say a const of GUI is equal to a new dat.gui all uppercase object. And we want to make sure that this is working as well. So what I'm going to do is I'm just going to console log this out. Always make sure your code works as you go about it. And here you'll see we now have a GUI object. So now that we have a GUI object, what we can do is we can call GUI.add, and the first argument here is going to be another object. And this object is going to contain all of the properties we actually want to start editing within our actual Three.js piece. So in order to put an object here, we need to create one. Right below this constant GUI, I'm going to create a new object called world. This is going to be equal to an empty object to start, but we need to think, what kind of properties do we want to start editing within our world? Well, we want data related to our plane, so let's go ahead and add a plane object in here. Set it equal to an empty one to start as well. Now let's think, what kind of properties does our plane have? Well, if we look back to our plane instantiation, we know our plane has a width, it has a height, it has a width segment, and it has a height segment attribute associated with it. So let's start off with just the width of our plane. We know our plane has a width, and to start, we're declaring it equal to 10. So our default value for width is going to be equal to 10. And now that we have this object available to us, we can insert it within our GUI.add function. So the first argument here is going to be an object. We want to select our world, and specifically our plane object. Now, what property within this plane object do we want to have a slider associated with? Well, that is going to be our width property. This is going to be equal to a string width. So now just by saving with this, you'll see that we have a number selector up here that we can start changing the value of. But let's say we want this to be an actual slider, not just a number value. Well, the third argument is going to be the minimum value you want the slider to be able to go to. So what is the minimum width our plane should have? Probably no less than 1. And what is the maximum value our width should have? This is going to be the fourth argument that GUI.add takes. We don't really know just yet how large we can go. Let's go ahead and just say 500 is going to be the max of our slider. And now you'll see our width by default is 10. Up here when we refresh, it's equal to 10 by default. And we can start altering this value with a slider because we inserted this 1 and this 500 as the third and fourth arguments within GUI.add. So as I begin changing this, the value changes for our world plane width. So this value is changing, but now we need to actually integrate it within our code so that when this changes, we are basically recreating our geometry with this new value. So our plane geometry is only instantiated, only called once, and that is on load because it's not inside any event listener or any function that would actually call it. So what we can do is we could say whenever we change the value of width within our world.plane, we want to regenerate this geometry. So at the very end of GUI.add, I'm going to change on a function called onChange. And this is going to have one argument. It's going to be an arrow function, a callback function, so that whenever this value changes, we're going to be calling this function. We can see this in action by consoling out our world plane width. And now whenever we change the width up here, we should be able to see it be changed within the console. So if I begin to change things, you'll see that that value is indeed changed as I begin to move the slider up and down. So we know we're creating a plane mesh, but when we change the value of our GUI slider, we want to select this plane mesh, and specifically we want to select its geometry. So let's go ahead and console log this out to make sure that we are getting this correctly. Put it inside of console log. We get rid of the second console log. We don't need that anymore. Save. It's going to refresh. We begin altering our slider, and you're going to see we are indeed selecting our plane geometry. But what we want to do is we want to set this plane mesh geometry equal to something new that takes into account the new width of the world plane that we have going on with our GUI slider. So the very first thing we want to do is we want to select our plane mesh geometry, which we're already doing, and we want to dispose of it. This is just going to get rid of it from the scene altogether, get rid of it from the mesh. And then the second thing we want to do is assign it a new geometry. So what geometry do we want to assign it? Well, we can go ahead and grab our plane geometry instantiation right here, paste it into our onChange callback, and we're going to say plane mesh.geometry is equal to this new 3 plane geometry. But we don't want to set our plane geometry equal to a static value with a width of 10. We want to make sure that we're setting this equal to the value we are getting from world plane width. So instead we can put in here world plane width. We save and then we begin to edit our value, and you'll see our plane begins to change as we edit its width. Now as I go bigger and bigger, it just goes off the screen completely. Not something we really want. It kind of makes all the values above, it looks like 20, a little useless. So what I'm going to do is I'm going to change our slider max to 20. And now this gives us a little more breathing room to get different values with the slider directly. Looking pretty good, but you'll notice as I decrease and increase the width, it did away with all of our vertice manipulation that we just worked so hard to get. And it only comes back on refresh. So although we're creating a new plane mesh geometry with a new width, something we are not doing with this new geometry is setting the new positioning of all the individual vertices. We need to make sure we do this again whenever we assign a new geometry to our plane mesh. So where are we altering all of our vertices? If we scroll down, it's going to be this for loop right here. So we can go ahead and copy this, go to our onChange function and just paste it in there. And let's watch what happens now when we change our slider value. You'll see it gets smaller and smaller, but all the vertices are still being edited in real time as we begin to change. And all we're really doing here is setting the Z position of each vertice to be something random each time this width value actually changes. So looking pretty cool, and this is giving us the ability to get the exact value we might want within our plane object. But we might not want to tailor just the width, we might also want to tailor the height as well. So a quick challenge, I want to challenge you guys to add the height property to this dat.gui instance. Pause the video, do so now. Otherwise, let's keep going. So to change the height with dat.gui, pretty simple thing we can do here is we can just go ahead and copy gui.add, create a second instance of it. So we know we want to change a property related to our plane object. Well, we don't want to alter a width property, we want to alter a height property. This is also going to be equal to 10 by default because that's what we have it to at the moment. And now we can change width to height. We can keep our height value equal to 1 to 20. That seems reasonable. We're going to dispose of our geometry and set it equal to our dat.gui width, but also our world plane height. That's pretty much all we need to do to affect the height of our plane. Let's watch what happens. If I begin to decrease the height, well, the height of our plane gets smaller and smaller, increase it, gets bigger. Same thing for width, both of these are going to work in tandem, but you might have just noticed a bug. Even though my height was set to 4, as I begin to change the width, Well, the height goes back to something larger. Why is that? Well, you'll see right here, where we are changing width with our slider, we're creating a plane geometry set to the new width that we have up here, but we're still setting it equal to 10, which was the initial default value. We need to make sure we are setting it equal to the dynamic value we're setting within world plane height, so we can simply change this equal to world plane height, save, and now decrease our height, decrease our width, everything stays relative to each other, which is exactly what we want. Now looking at this code right here is quite duplicative. I don't think there's actually any difference between our onChange callback functions within height and also width. So if you have a large portion of code that's exactly the same, that's a pretty good indicator that you should probably abstract it and put it in its own function. So we're going to do exactly that. What I'm going to do is I'm just going to copy all of this code right here that generates a new geometry for our plane and sets its vertices, and I'm going to create a new function called generate plane. And inside of here, I'm going to call all of the same code. So now instead of using this empty arrow function right here, I can call generate plane whenever we change our height, and things still work exactly the same. Now we can delete all of the code with our onChange for our width, get rid of the empty arrow function, put in generate plane just like we did for our height, and now our width is edited just like our height is, and they work in tandem together because they both use the same function. The function edits the plane geometry based on the world plane width. It also edits the plane geometry based on the world plane height. So let's go ahead and finish this off for not just width and height, but also width segments and height segments for our plane so we can get more geometry put in there in case we want it. So we know this value right here, the third argument within plane geometry, is our plane's width segment. So we'll know that we'll want to basically edit our world plane width segment. And this fourth argument right here, 10, that is going to be equal to not our width segments for our plane, but our height segments instead. Now these two properties don't exist just yet, so we're going to add them into our plane object up here. By default, we set our width segments equal to 10, and we also did the same thing for our height segments. That also is going to be equal to 10. So finally, we need a way to alter these. What we're going to do is copy GUI.add and say that we want to be able to alter our width segments property, and then we want to be able to alter our height segments property as well. Any value 1 to 20. So if we save that, we now get the 2 extra sliders, and if we begin changing these, you'll notice the amount of segments begins to decrease as we begin to decrease this value. And same thing goes for height segments. If we go all the way down to 1 for both of these, we're just going to get basically a plain square with no segments inside of it. But if we go all the way up to 20 for both of these, we get something that's really, really geometrized. I don't know the right word for it. Something that has way more polygons compared to the amount that we had before. And we can definitely increase this value by a little bit. Let's go ahead and increase both the max values for these by 50. Increase these. We get something that just looks really wild, which we can always reset if we just refresh the page. So looking at our to-do list, we now know how to modify our plane with dat.gui. So we're going to check this off as well. Now, before we go on to hover effect, there's one more thing I want to include in here. You might have noticed within the original project, over on this side, that I can actually select a portion of the screen, and if I start dragging while I'm selecting it, you'll notice that the scene changes its orientation along with me. This is what's called OrbitControls within Three.js, and I want to show you guys how to add that to your project as well, especially as you begin to alter your scene over here using dat.gui. So one thing I'm going to include in this is add OrbitControls. Let's go ahead and do that now. Adding OrbitControls is actually relatively simple, but the thing is they don't come paired with the Three.js library by default that we're already importing. This is actually something we're going to have to import separately, but thankfully we can import it using a very similar URL compared to what we have right here with unpackage and Three.js. So what we're going to want to do is we want to take this first portion of the URL, everything from HTTPS up to 3 at 0.126.1. We're going to copy this, and then we're going to try to visit it within the browser to make sure we are referencing the correct file. So we want to paste that in there. If we visit this right now, well, we are presented with some sort of version of Three.js, but we want just the OrbitControls because those come separately from Three.js. To get the orbit controls from this URL that we just pasted, 3.261, at the very end of this, we're going to want to paste in or type the following URL. So if I full screen this, you'll see that this is /examples/JSM/controls/OrbitControls. So basically we're going into the whole Three.js repo that also contains examples. Within this examples folder, well, we're going into an importable module called OrbitControls. If I go ahead and visit this, well, this is all of the code related to the OrbitControls object. So now we know this is the correct URL to pull from. So we can go ahead and copy this. And then right below where we are importing 3, we want to import specifically OrbitControls object from that exact URL. So if we save, then console log out OrbitControls like so, visit our app over here, we refresh. Well, it looks like this function right here is everything we need to create OrbitControls within our scene to begin moving around. And to instantiate OrbitControls, all we need to do is include what camera do we want to be able to move around our scene, and then what is the DOM element of our render. So below where we created our camera and also our render, we'll go ahead and do this right here where we're currently altering our camera's position Z. We want to create a new OrbitControls object, and the first argument here is going to be the camera you want to use. So it's going to be our perspective camera we are creating above, and then we want to select our render's DOM element. So we'll put that as the second argument. We save, and now when we begin to click and drag on our scene, you'll notice that it moves around in three-dimensional space. And as I begin to move this around, you'll notice even if I go to the backside, we're not seeing anything over there, even though we definitely turned on the double side rendering. Now, why isn't anything showing? It's simply because our light is only facing forward on this side of the screen. As we begin to move our camera to the other side of the mesh, you need to realize we're only moving the camera, we're not rotating the plane at all. But since we rotate the camera to the back side, there's no light over there, so we don't actually see the back side of our plane, even though technically it is right in front of us. So if you're wondering why you don't see anything on the other side, it's simply because there's no light over there. You can create a new light and push it to behind our plane, and let's go ahead and do that now, just to show you how this works. If we want to create a new light, we can simply copy these 3 lines of code. That creates a light, positions it, and adds it into our scene. This will be backlight. We're going to set our backlight's position to have a value of Z-1. And then we're going to add our backlight to the scene. So if we save this, and then start going to our backside now with that new backlight, we're going to see the backside of our plane simply because it's lit up. So if you're wondering why it's not there, you just need to make sure you add a light because of the material we're using. Only works if you have some sort of light on top of it. So now you are more than free to start editing your plane as needed while moving around your scene to ensure you get the exact look that you would like. So if we go back to our to-do, we now successfully added in OrbitControls. So only a few more things to do. We need to add in our hover effect and then add in HTML. Let's get the hard one out of the way by adding in the hover effect. So when we're adding in a hover effect, it's useful to have some sort of pseudocode in place to know exactly what steps we need to take in order to get there. So I wrote a few out, and the very first thing we need to do is add some sort of mouse event listener so that whenever we move our mouse on the screen, we are tracking its coordinates. We want to use these coordinates so our scene knows where exactly is our mouse relative to the objects on it. So one piece at a time, let's go ahead and start with adding in a mouse move event listener, and then we're going to do something called normalizing mouse coordinates. So going back to our code, whenever I add in an event listener, I typically like doing it at the bottom of my code because that way I know this is where all of my events are, at least events related to the window. So to add in an event listener, I'm going to type add event listener, which takes a string for the first argument. This is going to be the event you want to listen for. I want to listen for a mouse move whenever our mouse moves across the browser window. And what happens whenever we move our mouse? Well, whatever is inside of this callback function. If I console log out something such as move, so we begin to move our mouse, you're going to see that it's logged out on the bottom left-hand corner of our console. So we're going to need to be able to grab the X and Y coordinates from this event. To get those coordinates, we can select our event object, which is always going to be passed through as the first argument within this callback function. So if I console log out event.clientX, we're going to get the X position of our mouse as it moves across the browser window. you'll see now, if I go far to the left, mouse is equal to 0. If I go far to the right, it's equal to about 640, which is what this browser width is set to. If I want the Y coordinate, all I have to do is change client X to client Y, save, refresh. Now the higher I go to the top, the closer we get to 0, and the further down I go, the larger this number gets. So we know we want to use client X and client Y outside of this mouse move function. So what I'm going to do is I'm going to create a mouse object. Mouse is going to be equal to an empty object with an X. It's going to be equal to undefined to start, an X coordinate, and then a Y coordinate, which is also going to be equal to undefined. These aren't going to be defined until we actually move our mouse across the screen. So here we can say our mouse X is equal to event.client X, wherever it is on the screen whenever we move the mouse. And then our mouse Y is going to be equal to event.client Y. Save, and then we console log out mouse and start moving. You'll see now we're getting the coordinates for both X and Y no matter where our mouse is on the screen. The closer we get to the top left hand corner, the closer we are to 0. Now the issue with this is if we want to use a raycaster, well, the raycaster uses what's known as normalized coordinates. The coordinates we're using right now are not normalized because the center of the axis is the top left hand corner of the screen, which is the default for browsers and websites, but the default for Three.js, the center of the screen is right in the middle of the screen. So whenever our mouse is in the center over here, X and Y need to be equal to 0 so that the raycaster is actually positioned correctly to understand where our mouse is pointing relative to the plane we have on the screen. So basically we need a way so that the further we move from the center of our screen to the left, we get a value of X is equal to -1. As we begin moving to the right, we should be getting a value of 1. So we need to change our coordinate system from -1 to 1 within our mouse move function. So to start, what I'm going to do is I'm going to divide client X by our Windows inner width. Let's go ahead and see what we get with that. If I begin moving further to the right hand side of the screen, it looks like this might actually work. The further and further I go to the right, you'll see X is getting closer and closer to 1, which is a good normalized coordinate from 0 to the right hand side of the screen. But as I start going to the left, as we get to the center, well, this should actually be equal to 0 for the X coordinate, not so much 0.5. And the further left I go, we need to make sure that the left hand side is equal to -1, not something near 0. So to save you guys some headache in the math you need to do for this, what we can do here is we can put this inside of parentheses, multiply it by 2, and then subtract 1, and that is going to give us normalized coordinates for the X value. You'll see as I begin going near the center, X is equal to 0. As I begin going to the left, X is equal to -1, and the further I go to the right, X is equal to 1. So that's exactly what we need to start interacting with our mesh in 3D space. But we also need to do the same thing for client Y. So you might think we can simply take this code right here and paste it in and set mouse Y equal to it while changing client X to client Y and inner width to inner height. You might think this works. Let's go ahead and watch what happens to our Y value. As I begin to go down, you'll see that Y is getting closer to 1. And you might think, well, isn't that what's supposed to happen? Isn't it supposed to get closer to 1 as you go down? Within the coordinate system of Three.js, the further you go down on the Y-axis, the more negative your number should be getting. So we shouldn't have a positive number for Y as we go downwards. We should actually have a negative number. Same thing for when we go upwards. Y should be equal to something positive here instead. So all I need to do here is instead of subtracting 1, we're going to add 1. And the value of client Y divided by inner height, we're going to set this equal to negative to basically reverse the direction in which our Y coordinate is being read. So if I save that and we start going down from the center of our Y axis, you're going to see our Y value is getting closer and closer to -1, which is perfect. And as we go closer towards the top, it's getting closer to 1. So now we have normalized mouse coordinates that we can use within our Three.js scene, but we now need to use something called a raycaster. Let's look at our to-do list real quick. We added in the event listener, we normalized mouse coordinates. Let's go ahead and import that raycaster. So luckily for us, we don't have to import anything separate here like we did for OrbitControls. All we have to do here is import the raycaster directly from the Three.js library. So where we are importing our scene, camera, etc., I'm going to create a const called raycaster. This is going to be equal to a new 3 raycaster. So we can always console log this out to make sure it's working. Safe way to do things. There it is. We imported the correct object. Now let's go ahead and use this to test where our mouse is relative to the objects on the screen. But first, what is a raycaster? Whenever I think of raycaster, I always think of a little laser pointer that's always being pointed from wherever our mouse is on the screen directly into the 3D space. A raycaster is just an object that tells us where our little laser pointer dot is relative to the scene. So if I move my mouse off of our object over here, our raycaster is pointing its laser pointer over there. Therefore, it's saying our dot isn't touching anything. If I move it on top of our plane over here, well, our dot is touching the plane, so the raycaster object is going to say, red alert, our laser pointer is touching something. And it's going to be able to monitor touches for pretty much anything that we have on the scene. We only have one object right now, so this is all it's going to monitor. But if we had multiple objects, the raycaster has the ability to monitor whether or not it touches those objects as well. So within our animate function, this is where we want to check whether or not our raycaster is intersecting with our plane. So we're going to select our raycaster, and we're going to call its set from camera function. And this takes 2 arguments. One, it takes our mouse, our normalized mouse coordinates, which we already took care of within our event listener. And 2, it takes a camera as a second argument. So if we save this, you'll see we're getting an error, cannot access mouse before initialization. This is simply because we declared the mouse constant beneath the function we're using it at. So we just need to make sure that we are declaring it in a position above animate, which if we move it up there, you'll see we don't have that issue anymore. And we still get our mouse coordinates being logged as so. So now that our raycaster, our laser pointer, is being pointed from wherever our camera is pointed towards, since we use this set from camera function, what we can do is we can call raycaster.intersect object. What object do we want to test whether or not our laser pointer is touching? Well, that is going to be our plane mesh. We're going to store this in a constant called intersects. So now if I console log out intersects, you're going to see it's equal to an empty array. But as I begin to move our mouse, you'll see our coordinates are being logged. But if I begin to move over our plane, you're going to see we're logging out some sort of object within this array. And if we look a little deeper inside of here, well, it just so happens that this object is our plane mesh. So to make this a little more clear, let's go ahead and delete this console log mouse within our event listener. Refresh, put our mouse over here. So nothing is intersected just yet, but if I begin to move over our plane, you'll see now it is tracking that we are indeed moused over it. And the cool thing is, since this is set from camera, if we begin to move our camera, well, the scene is automatically going to take that into account. If I start moving my mouse up here, where the plane would have been beforehand, we're not tracking any intersection just now, but as I begin to move my mouse onto the plane, you'll see we are indeed tracking it. If I move it off, well, it's no longer there. So that is how you're going to start tracking whether or not your mouse is over certain geometries within your scene. And to create a conditional in our code for this, what we can do is we can say if intersects.length is greater than 0, we could say that we are intersecting. Start moving, we're intersecting, we go off, we're no longer intersecting, and so forth. So this is where the code is going to go that changes the color of our plane as we begin to move our mouse over it. So looking at our to-do list, we imported our raycaster and we tested for intersects. So based off the intersected face, now all we need to do is change the surrounding vertex colors. Now, when we hover over our plane, we want to make sure that we're changing the colors of the faces that we hover over. So we have a way to test the hovering, but now we need to actually change the colors of the vertex, and it creates this nice little spotlight effect over your mouse as you begin to move across the plane. What we're really doing here is we're changing each individual vertex color, which actually spreads out and creates that nice spotlight effect, rather than changing each individual face. So how do we go about doing that? Well, let's go ahead and go back to our project, and we're going to want to focus on one of the attributes related to our plane. So back where our plane geometry is being created, we have 2 places in which this is being created in. One is going to be within this generate plane function, and if we look a little further, we're also by default creating a plane geometry. whenever we load the page. So if we scroll a little bit further down within this load code, you'll see here we're already altering one of the attributes related to our plane mesh geometry, and that attribute is position. Well, let's go ahead and console log out our plane mesh geometry attributes and see what's available inside of there. If we go ahead and console log this out, this is going to be our plane mesh attributes, and we look inside. Well, we have 3 attributes available to us. We have a normal, a position, and a UV. Now, normals and UVs, those are a whole nother topic. We don't need them for this video, but position is obviously where is the vertice in the 3D scene for the X, Y, and Z coordinate. Now, these are the 3 attributes that come with the geometry by default, but there is one that doesn't come with it by default, but actually one that we can add into this attribute object, and that attribute is going to be a color attribute. So if we want to add a new attribute into our geometry, well, the first thing we need to do is select that geometry. So we can reference our plane mesh geometry. We'll go ahead and paste it below. And then we want to call a function called setAttribute. The first argument for this function is going to be what attribute name do we want to set. Well, we already have one for normal, position, and UV. This one we want to set is going to be color. And what is an attribute within a geometry? Well, we can kind of get an idea for this by looking at the current attributes. Well, they are going to be a float32 buffer attribute, which if we actually look inside of one of these, it's basically an object full of all the data related to this array. And this array for position specifically contains all the data for the vertice positioning. They're just in groups of 3s, which we went over a little earlier. So the second argument we want to put in here is what kind of attribute are we creating? Well, we're going to be creating a float32 buffer attribute. And to create a float32 buffer attribute, we want to reference a new 3 buffer attribute. And this buffer attribute takes a float32 array. So to create a float32 array, this is basically just a typed array with JavaScript. Typically you can just type an array in like this. This is an untyped array. Types are assumed. You can put different types in if you want, such as a string or a number. But with a float32 array, we actually need to create a new float32 array object. So basically inside of this, we're going to put an untyped array. And when we put an untyped array in here, well, it's going to make sure that all the numbers within this array are of the type float32. And that is just something that's required in order to get this buffer attribute working. Now, if I save this, there is another argument that we need to add to our buffer attribute instantiation. So right after float32 array, at the very first ending parentheses, we need to add a comma. And then what is this last argument? Well, it's going to be a grouping number. How many numbers within this array consist of a group? And we look inside of our array. We know that every 3 indices here represent one position, an X, a Y, and a Z. Basically this right here, this number, is the item size. It says how many of these data pieces right here consist of one grouping to represent one value. Position has an X, Y, and Z. 3 data types. So if we were to do position right here, it'd be 3. But if we think of what a color attribute consists of, it's an R, G, and a B. If you set those 3 values, then you're going to be able to set the color of whatever it is you want to affect. So since RGB is equal to 3, every 3 data pieces we have within our array is going to be one representation of one vertice color. So we can just add 3 here within our new buffer attribute creation, and we should be set to start altering our vertice colors. So into our float32 array, we're passing in 3 values. This first one is going to represent R, the redness of our actual vertex. And the values for this are anywhere from 0 to 1. It's not actually 0 to 255 like you might be used to for RGB values. So instead of using a 3, we need to make sure that we specify any value 0 to 1. Let's go ahead and make a specific vertex a different color. Let's go ahead and make it blue. If we want to make one specific vertex blue, we're going to give it a value of 0 for red. We're going to give it a value of 0 for green. And then we're also going to give it a value of 1 specifically for that blue data value. So if we save this, you might be expecting, since we're only altering one vertice right here because we only have one grouping of 3 RGB, that the very first vertice up here should have some sort of blue color associated with it, which it doesn't. The reason being, even though we have this color attribute, which our plane will read, we need to make sure that we go back to our plane material right here and declare that we want to use vertex colors. We're going to set this equal to true. And you'll see once we set that to true, well, our plane just disappears completely and we end up getting an error in the console. This is occurring because right now we're only supplying the color for one vertex. In order to actually get this working, we need to supply colors for every single vertex within our plane. So in order to ensure we are supplying a color for each vertice within our plane, we first need to know how many vertices does our plane have in the first place. Well, we can find this by looking within our plane mesh geometry attributes. If we look inside, we now have an attribute for color, which is great. You'll see we're only supplying just 3 pieces of data to our color attribute, when in reality, if we look within any of these other attributes, there should be 336 pieces of data. And when we group each piece of data within this array into 3, well, there are going to be 121 groupings of 3. We need to do the same thing for our color attribute. We need to make sure that this array right here is equal to 363, and that its count is equal to 121. Our item size is already 3, meaning that this grouping right here represents one value of RGB. We need to make sure that we extend this array. So how do we do that? Well, the first thing I'm going to do is I'm going to create a constant called colors, and this is going to be equal to an empty array. The second thing I'm going to do is I'm going to create a simple for loop, and we're going to be looping through our plane mesh geometry. We're going to select our attributes, which is everything we see right here, and then we want to dive into our position attribute. We can say we want to loop about 121 times. That's how many groupings of data we need in order for this to work successfully. So if we go ahead and console log out I within this for loop, it should go up to 121, which it does because remember 0 counts as 1, so that is working correctly. But now we need to push some colors into this array for each vertice. So if we select our colors array, and then push in an R, a G, and a B, watch what happens. This is going to be affecting every single vertice because we're running it for every single vertice based off of our position attribute count. So if I save this, we're not going to see anything, but if we go ahead and console log out, our colors array should be filled up with 363 pieces of data. All of them are going to be blue because we set the R to 0, we set the G to 0, but the B value, blue, is going to be equal to 1. So how do we actually use this and set it equal to our plain colors attribute? Well, right now we're only passing through the simple 3-value array. We're going to go ahead and get rid of that, and we're going to push in our colors array, which we just populated with everything we need. We save, and everything turns black. Now right now, since we just added in vertex colors, a color for every single vertice within our plane, what's happening is that color is interfering with the initial color we put within our mesh fog material. So when we're adding in vertex colors, what we can do is we can take out the initial color we assigned, and now our material is going to reflect the color we assigned with the vertice color instead. So now everything is blue. If I go ahead and change our vertices to something else, such as green by changing the values right here where we're pushing into our colors array, save, you're going to see everything is green, and then everything is going to be red initially if we set it equal to 1, 0, 0. So now that each individual vertice has a color associated with it, what we can do is when we hover over a piece of the mesh that is close to one of those vertices, we can change that one individual vertice color to be something else, and that's what's going to give us that trail effect as we move our mouse. So where are we actually tracking whether or not our mouse is hovering over the plane? It's going to be right here, where intersects length is equal to 0. So this is where we intersect, but this is also where we're going to be changing the color of each individual vertice. So here, if we look inside our intersects array, this is an array because you might be able to intersect multiple objects, we're going to want to select the very first item in the array. And of course we're going to have at least one item because we're testing that we have one item right here. And I hover over this and open this up, you're going to notice that this has a face property inside of it. This is the exact face that we're hovering over. If I zoom out a bit and hover over this very first face in the top left-hand corner and make sure I am opening up that object right here, you're going to see that face consists of 3 properties, A, B, and C, and A, B, and C are representative of a grouping of data. So for instance, let's go ahead and say our color attributes are equal to something like this, and of course we're going to have more data at the end of this. Let's go ahead and look at this. Well, if we hover over this top left hand corner and it gives us an index of 0, a grouping index of 0, well, it's going to be referring to these 3 values right here. this first grouping. If we look at C, that is going to be referring to basically the second grouping because we're using indexes, which we always start at 0. So if we go to the second grouping, it's going to be these numbers right here. And if we were to go to 11, well, then we'd be referencing the 11th value within this iteration, which would be further down the line, something over here. So when you hover over a face, it's returning to you which group of data points make up the face that you're hovering over. One vertice here, one vertice there, and one vertice there create a face. This is the index associated with each of the groupings within your attributes array. So what we're going to want to do is we want to select this face attribute that we get whenever we hover over something, and we're going to be using the A, B, and C here. And one of the other things we want to select, let's go ahead and comment this out for now. One of the other things we want to select is going to be what we're hovering over, which is going to be the plane. We want to select the object, and specifically its geometry. If we go ahead and save this, hover over it, looks like I just spelled intersects wrong. Go ahead and make sure we spell that correctly. We hover over it. Well, now we're getting our plane geometry. And since we're accessing our plane geometry, we can get all the vertex attributes associated with it. So we're going to go into our attributes object, and then we want to make sure we select our color attribute. We hover over this, and now we have our buffer attribute object, which contains all the color data related to each individual vertice. So let's say we stick with hovering over this top left-hand face over here. If we're to hover over that, we want to make sure that we're changing these three values within our color attribute array. So how do we do that? Well, we're going to want to select our color attribute, which we have right here, and it has a nice little function that we can add on to the end of this, such as set x. And the first argument here is what index grouping do we want to select? Well, we want to select this first index grouping right here, which is going to be 0. And then to what value do we want to set the X color of? So when we refer to X, it's going to be the very first value within this grouping. You can think of X as being R. What do we want to set the R attribute to? Well, we can go ahead and set it to 0 whenever we hover over it. And when we hover over our plane, zoom out, we're not seeing any color change in the top left-hand corner just yet. And that is because when you select your geometry attribute color, you need to make sure that it knows to update the color based off of the action that just happened. It needs to know that the data within its array changed. So what you can do is you can select that color attribute, give it a property of needs update, and set it equal to true. And once you do that, and then hover over your plane, scroll out, you're going to see that one vertex now has a color of black rather than red. We just set the R value, which right here is X, it's just a shorthand method. We just set the R value to 0 instead of 1. So if we look within our color attributes array at the very top, open this up, you'll see that we are giving the first vertice up here a value of red to start. And then when we set its X, its R, so these first three groupings, we set this one value equal to 0 because we're selecting the first grouping index, which is these three guys right here. And we want to say set X, the first value, equal to 0. We change this 1 to 0. That is what makes it black in the top left-hand corner. So instead of selecting just the very first vertice and altering that, we want to make sure that we are selecting all the vertices related to this face and altering all three of those instead. And thankfully, we can already get all the vertices related to the face we're hovering over by using intersect 0 face. If I console log that out, remember when we hover over this, we get each index related to the face we're hovering over. So using this, we can go ahead and copy intersect 0 face. Instead of setting our index at 0, we know the exact index we want to set by using this right here. So now if I save, refresh, and start hovering over, we're not seeing anything just yet. And if we put only face here, we're only getting the whole object of face, which is A, B, and C, all the indexes related to it. But we want just one vertice at a time, so we want to make sure we select the very first vertice of the face we're hovering over, which is going to be A. That's going to give us the grouping we need. And now, if we start hovering over this, you're going to see that the very first vertice of whatever face we're hovering over is going to be turning black because we're setting its red attribute to 0, which is indeed what we want to create this effect. But right now it's a little janky because we're only setting the color of one vertice related to our face. You'll see right here where my mouse is, we only set this one vertex right here to be black, but the top right and the bottom vertices don't have their vertex colors changed. We want to make sure we're changing all the vertice colors for the face we're hovering over. So we only did one, which is the A value of face. We want to make sure we're doing the same for the B and the C values of our face as well. So all we need to do here is we copy this line of code, and we want to make sure that we change face.a to face.b to make sure we're changing the color for that vertice as well that we're hovering over. So now we have two vertices changing their vertex color, the bottom left, the bottom right. We just have one more to go, which is going to be the top one. We need to make sure that we're also referencing our face.c, and those are all the vertices related to that one face we're hovering over. So we save, and now all the vertices of this one polygon right here, this one face, should light up as black, darken as black. So we hover, and now all three vertices are indeed black, and it creates for a much smoother effect with everything lighting up as you would like it to. So looking at this over here, this code is pretty sloppy just because we're duplicating our code many times. This is a very long statement. It's hard to read. So something you can do to make this a little cleaner is object destructuring, which we went over a little bit, I believe, in this video already. What I'm going to do is, we know we need to select the color attribute related to our object geometry, which we're selecting using this long statement right here. So what we can do is we can just go ahead and cut this out of where it is and assign a const of color, which is going to reference the color associated with this attribute's object. If we do things like this, well, now we can easily read our code to say we want to set our color's X value, or R value, equal to whatever code we have right here within its argument. And we can go ahead and do the same thing by getting rid of all this extra code right here, because we're already referencing the geometry attribute's color. We do things like this, things are going to function exactly the same, but obviously this is a lot cleaner as before, because now we just have a small color constant instead of that long beefy statement with intersects object geometry and attributes. So right now we're only setting our red value equal to 0, which in return gives us a black hover effect. What if we want to change that to a different color? Well, we need to make sure we're not just setting the X value, the R value for our face vertex. We also want to make sure we're setting the G value, which is going to be Y. If we use the function set Y, we're going to be setting the middle piece of data within our array. Let's say our array consists of this. Right now to start, RGB. If we use set Y, we're going to be setting this middle value right here. So if we set this equal to 1, our green value is equal to 1, and we set red to 0, which we're already doing right here, well, now our hover effect should be green for the vertex we're hovering over. So let's go ahead and do that. We're going to set that middle value for our face A equal to 1. Let's watch what happens. We start hovering over things, and at least one of the vertices is turning green. The others are still turning black because we haven't taken into account the other vertices. To make this a little easier, we can comment out vertice 1, vertice 2 for this code, and then this last set X is going to be equal to vertice 3. So if we want to make sure we're not just changing vertice 2 equal to black, we need to make sure that we're also setting its Y value, its G value, on face B equal to 1. So now we only have one black vertice being set. Let's go ahead and change that as well. We want to set that vertice on face C so that its green value is equal to 1. And now everything is going to highlight green as we begin hovering over this. And you can go ahead and do the same thing for blue by setting the face A vertices Z, the third data value within the array, equal to a value of 1, and this is going to change it blue. You want to make sure you do this for every vertice within the face you're hovering over. So we set Z here for face B equal to 1. We change the green back to 0. We do the same exact thing for our last vertice. Change it equal to 0. We should get blue when we hover over this. And it looks like we do. And I just messed up a little bit here. Right now we're setting green equal to 1 for that one vertice. We're going to change that to 0. Make sure that blue is 1 instead. And now we get the hover effect we're looking for. So this is exactly what you want to get some sort of highlighted hover effect, is to add in your color attribute, make sure it's populated correctly, that your material has vertex colors turned on, and that you set the vertex color equal to a new one within your raycaster intersects conditional. I know it's a lot, guys, and I'm sorry if that's a little confusing. It's a lot to take in at once, but this is currently the easiest way that I'm aware of to get the effect you want to get. It's probably a little harder than Canvas, but hopefully I explained that in a way that makes a little more sense than it would have trying to learn that on your own. So if we look back at our to-do list, well, we successfully added in a hover effect, and we are changing the surrounding vertex colors based off the intersected face we're hovering over. So you might think, well, can't we just go on to HTML now? Well, not quite. There are still a few things that we want to do to make this look a little better and start matching up with what we have over here. The first obvious one is we want to change the color of this to match something over here. This looks like kind of like a river or ocean of some sort, which I really like. So I want to make sure that we're changing our color to match up exactly. So how do we change our color to match up with something along the lines of an ocean? Well, where are we changing the color by default for our plane? Within our material is created right here, mesh falling material. We took out the color attribute because it was interfering with our vertex colors attribute. So right now, the color of our plane is determined by our vertex colors, which if we scroll down, our vertex colors are determined right here. By default, they're going to be the R, G, and the B value we're pushing through into our colors array, and then setting as our color attribute for our geometry. So here we can give RGB values to be the exact color we want our plane to start out as. And to save you some time, to get the exact color we're looking for over here, those values are going to be 0 for R, 0.19 for G, and 0.4 for our blue. That's going to give us this nice ocean-like blue color. Hover over it. Well, we're still getting a neonish blue hovered over it because we haven't changed the color of our hover effect. So we scroll on down where we're changing each vertex color within our animation loop. These three values, R, G, B, are going to be representative of the color we want to add in whenever we hover over our plane. And to save you guys time here, to match up the color of this light blue, we want to make sure that we supply an R value of 0.1, a G value of 0.5, and then a B value of 1. And we want to make sure we're doing this for each vertex of the face we're hovering over. So it's going to be 0.1, 0.5, and 1, and then 0.1, 0.5, and 1 as well. We save this, we go back to our app, and now when we hover over this, you'll see it has that same light blue color that we have over here. The only difference is, when we hover over things, eventually the color changes back to normal. To do this, what's happening is each face we're hovering over, we're setting the color equal to the new color we set within vertice 1, 2, and 3. But as that is being set, we're also calling an animation function to fade the vertices back to their initial color. And we can do this using an animation library called GSAP if you haven't heard of it. So GSAP is the go-to for creating animations without much headache. To install GSAP, we're going to be using the terminal method the same way we installed vite and dat.gui. So what we're going to want to do is open up our terminal, make sure that you're inside of your directory for your project, and then we're going to run npm install GSAP. Make sure that you save this so that it is installed as a dependency. Once it installs, you'll see that it should be listed out within your dependencies within package.json, and now you can import it into your main.js file. So if you want to import a library, it's typical to go to the very top and write import. For here, GSAP, we're going to be importing a GSAP object from the GSAP library. And remember, we can always test that it was imported correctly by console logging it out. We go back to our app, look within our console, scroll to the top. You'll see right here, this is actually the GSAP library that we can begin using. So now that it was imported correctly, we can go back to our intersect code, which is going to be down here. So we're going to be changing all the faces vertices equal to a light blue, but after that change happens, immediately after that change happens, we want to animate it back to its original color. So using GSAP, we can call a to function. This is going to be, what do we want to animate to? What do we want to animate in the first place? The first argument here is going to be an object. We need to create an object that consists of the RGB values of our initial color. So what was the R value of our initial color? If we forget, we can always scroll back to where we are setting our RGB values for each vertex, which is going to be right here. So R is going to be 0, G is going to be 0.19, and B is going to be 0.4. So let's go ahead and remember that. R is 0, G was 0.19, and B was 0.4. So we have an object for our initial color. We're also going to want an object for our hover color. This is what we want to change our value to. So if we look at our R is simply 0.1, our G is simply 0.5, and then our B is simply 1. And we want to make sure we're not calling this initial color, but hover color instead. So we know when we hover over this, we're changing the vertices equal to this color. So the vertice is currently equal to what hover color is right here. We want to animate these values down to our initial color instead. So what we can do is we can select our hover color object, and then for our second argument, we're going to be adding in two curly brackets to represent an object full of values. Well, what properties does hover color have? Well, it has an R, it has a G, and it has a B. These are the values we want to animate. But to what value do we want them to animate to? Well, we have those values right here within our initial color object. So we want to make sure we're bringing point 1 down to 0. So what we can say is we want our hover color R to go down to our initial color R. We don't want it to stay at point 1. We want to do the same thing for our G and B values. So hover color G is going to go down from 0.5 to 0.19, and then hover color B is going to go down from 1 to 0.4. So this is going to interpolate these numbers right here down to here, and we can see this in action by adding in an onUpdate property that is assigned to an arrow function within our second argument object right here. If we console log out, update to start, and begin hovering over this, you're going to see update is called multiple times because this is running an animation. Let's go ahead and log out the values of our hover color. Hover over this, and you'll see that those values are slowly shrinking towards 0.19 and 4 over time. Even if we begin to hover off of this, this is still going to run. It doesn't matter if we're no longer intersecting the plane. But why isn't the color actually updating whenever we hover off of it? Well, although we are changing these values right here to go back to the initial color, we're not actually setting the values within our geometry. We need to make sure we're doing that. So all we really need to do here, we are going to select where we are setting our 3 vertices, which is right here, and we're going to be pasting that in to our onUpdate function. And now, since we are setting our vertice colors within here, we can reference the value that is being interpolated, which is going to be initial color R, initial color G, initial color B, and we want to do the exact same thing for these 3 guys right here. And if we save this and start hovering over, you're going to notice, not really working, and that's just because another mistake on my end, happens from time to time for sure, is remember, we're not animating the initial color, we're actually animating the hover color. So if we want to get that smooth interpolation, we need to make sure we're setting the vertice colors equal to our hover color for each frame this animation runs. So now if we save with the hover color and begin hovering over this, you're going to see it has that nice fade out effect over time and eventually goes back to our initial color, which we declared right here. So really cool thing to get that water trail effect. So looking good, one of the last things we want to do in order to get a good homepage is we want to make sure we tailor this to the exact dimensions we want when a user lands on it. So if I were to change my width or my height, you're going to notice that our background turns black and it doesn't have any hover effect associated with it. We also get a bug in the console. Now, why is this happening? Well, let's go ahead and inspect where we are setting the color for each individual vertice. Well, let's get rid of some console logs, clean up our code a little bit. You're going to notice that we are setting the color for each individual vertice right here. But whenever we affect our width or our height, well, we're calling that within our generate plane function, as you can see right here with GUI add. So we need to make sure we're also calling this code right here whenever we are generating a new plane to ensure that it has the new vertex colors. So one simple thing we can do is we can just copy this code right here, scroll on up to where we are generating a plane, get rid of any excess code we don't need. And after we are setting the new positioning of our vertices, we can go ahead and set the color of them as well. So now when we affect our width, we maintain that color. When we affect our height, we maintain that color. And we still have the hover effect. And the cool thing is this works no matter how many segments we have or what width or height we have as well. We still have the same exact hover effect occurring. So how would I tailor this piece right here to look something more like this on a refresh? Well, the very first thing I would do for sure is I would enlarge this to the correct width or height. So if we go ahead and enlarge this, well, that goes ahead and it reaches the edge of the screen, but now we don't have as much dimension here because we don't have as many segments. So if we begin turning our segments up for both width and height, let's go ahead and just find something we like. I personally like a little more segments than a little less. I think that looks good. We'll go ahead and call this 19, 19, 17, 17 for something that I personally like. You can set this to whatever you guys would like on your own. So if I want to change the default in which this plane is spawned at, well, where am I creating my plane geometry? It's going to be right here, new 3 plane geometry, and we have all these hard-coded values. So really, for our width, I'd want to put in 19. For our height, I'd want to put in 19 as well, matching them up with what we have in the top right-hand corner here. And then I'd also want to change my width segments to 17 and my height segments to 17 too. So if I save this you're going to see that the plane spawns with these new attributes, which is perfect. But one issue is now the defaults for our dat.gui object up here aren't the same. They are not matching up with what they actually are. So to fix this, what we can do is we can go back up to where we are setting our plane object, and we're going to change our default width to 19, our default height to 19. I believe width segments was 17, and same for height segments. And if you don't want to have to keep changing these in two places, you can go back down to where you are setting the attributes for plane geometry, and you can just reference the dat.gui object directly. So it was world, plane, and then width. So this should maintain the width assigned for dat.gui. You'll see we have a width of 19 still. That is perfect. We can do the exact same thing for our height, and then the exact same thing for our width segments, and then our height segments as well. So on save, now we are referencing all the data from that data object up top, and if we want to change the default value for both our plane and the values for the sliders right here, all we have to do is change the value within this plane object. You'll see the default changes, and the plane actually changes as well. So that's perfect. That's exactly what we want. We'll go ahead and maintain what we came up with, which is going to be 19, 19, 17, 17. So now if I go ahead and exit out of this, it's always good to test what this looks like in full screen as well, see if that's something you like. I think that's pretty good. Honestly, I might expand this just a little bit more. So what I can do is, if I want to expand my width and height, I can change the max value for our width to be something a little larger, something like 50 for both width and height. And now I can expand my width and height and play with this a little more. Let's go ahead and make it something like 24. And I want more segments. 24 and 25, 25 is probably something I'm pretty happy with. And now you can see, since we have the OrbitControls in place, if I click and drag, well, we have this nice plane laid out, and you can always expand this more by playing with your width and your height attributes over here to make it a little larger based on whatever you'd like. And the very cool thing is with Raycaster and the vertex effect, well, the hover works no matter which angle we move our object at. So really, really cool stuff right here to play around and create this geometric background. So we tailored this to the exact dimensions we want, but one thing I actually forgot to add in here, I'm going to add this in now, is add vertice movement. So if we look at the original, and we scroll in, you'll notice that these vertices are actually moving in randomized directions, but they're not actually going off the screen or affecting the plane in some way to where it just doesn't look good. They're just moving in a controlled motion around each other, and it creates for this really cool kind of wave-like effect. Here, we don't have that. You could technically get away with this if this is what you want, but if you want to add that movement effect, well, we're going to need to do a little bit of editing, specifically within our animation loop. If you want something to move in a controlled motion back and forth between a specific point, one, you're going to need to use sine or cosine functions. Those are two functions that are always going to return a value -1 to 1, and since they always pulse between -1 to 1, we can affect a certain position to pulse between two specific points. And two, we need to be able to track the original position of the vertex. We always want to reference that when using math cosine and sine functions, because the actual position of the vertex is going to be changing. We need to make sure we're referencing the original position of the vertex to get some sort of pulsing effect. So that's going to be the very first thing we do, is we're going to store the original positioning of each individual vertice within a new array. So if we scroll on down to where we are setting our vertice positions, I'm just going to add that in here, vertice position randomization. And I'm going to add a quick label right here, color attribute addition. Just so I know what this code does, makes it a little easier to read. Here we are only setting the Z positioning for each individual vertice. If we'd like to randomize this a little more, we can change this so that we're also setting the X and Y to be a little more randomized. So let's say we want the X position of this vertice to be somewhere over here or over here. Just randomize things a little bit. Well, first we would have to select the X position, which is always going to be the first iteration of what we're looping through. You'll see right here, array I is equal to X. So we're going to be setting X equal to the current X value plus math random. Now math.random returns any value 0 to 1, any randomized value. But if we add that 0 to 1 onto this point right here, well, that's only going to push it in the right direction. We need to make sure that we're able to get a randomized negative value from this as well. So if you subtract 0.5 from math.random? Well, let's think. If we subtract 0.5 from 0, well, we have a value of negative 0.5. But if we get the high end of math.random, which is going to be 1, we subtract 0.5, we're going to be getting a value of 0.5. So this is a good way to get a random value anywhere from negative 0.5 to 0.5. But it might not affect the vertice as much as we want it to. If you want to affect this a little more, you can always multiply it by a larger number, such as 2 or 3. And that's really going to alter the x position of your coordinate. I think 0.5 was fine, honestly. So we're just going to go ahead and stay with that. And let's go ahead and also alter the y positioning as well. To select the y positioning, what do we need to do? We need to select I plus 1, that is the y coordinate. Make sure we are using the current y coordinate and then adding on a math.random value minus 0.5, so we get a negative value as well, possibly. And that actually looks a lot cooler than we had it before. But remember, to add in that animation, we need to store the original position and then alter this position right here. These positions are what we need to alter within our animation loop, but we always need to reference some original position. So to create an original position, what we can do is we can select our plane mesh, get our geometry, go to our attributes since we want our position attributes, and it's always good to console log this stuff out to see what exactly are we dealing with. So if I were to console log this out and look in our console, you'll see that this is console logging out a float32 buffer attribute. Inside of here we have quite a few properties, including the array that we're going to be editing to affect the actual movement of this vertice. But what we can do is we can add an additional property in here that is just a duplicate of the array that is never going to change, but we're going to be referencing that duplicate to create that movement effect that goes back and forth. So what I'm going to do is I'm going to select our attributes.position, and I'm going to create a new property called original position. And all this is going to be is equal to our position attribute, and specifically the array inside of it. So now when we log this out after setting this, we can open up this object again, and now we have a new property, original position. It is the exact same thing as our array, which contains all the data properties for editing each individual vertice. So to start animating these, we want to go to our animate loop, which is going to be right here. And we want to make sure that we're looping through this array, which is our positions attribute array. So we're going to do this above our array caster. This doesn't require any intersection or anything like that. We're going to create a for loop. And what is our array length? Well, what do we need to access? We need to access our plane mesh, its geometry, its attributes, specifically its position attribute, and then we want to access its array. This is how many times we're going to loop through this. And remember, whenever we have an array, we need to specify its length to get an actual number. So we're going to be looping through this about 2028 times. And if you want to clean up your for loop, remember, you can always take that long object property and use object destructuring to grab the array and set it to a new constant. So here, we can just reference the array directly with a small version of it and get its length. So right now we're looping through that giant array about 2028 times for every frame. To make this a little more performant, we can just select each data value as groups of 3 because we know each position has an x, a y, and a z. So same thing like we did earlier for one of the groups. Instead of adding 1 onto this for loop, we're going to be adding on 3. So now we're looping through substantially less times. And here we want to set our position for x, y, and z to be something different over time. So what we're going to do is we are going to be setting our array I. This is always going to be the x coordinate. And to get some sort of pulse effect, this is going to be equal to the original value. And remember, the original value is within this position object. So not only can we reference our array through object destructuring, we can also reference our original position. We're just pulling it out of this position object. So what we can do is we can set our array equal to the original position I. So basically the x coordinate of this is exactly the same as the x coordinate of this, but to create a pulse effect, we always need to alter the original value without actually altering the value that actually moves the freaking thing on the screen. So if I save this and refresh, nothing's going to happen, nothing's going to move. But if I add on to this original value over time, a math.cosine function, which takes an argument of radians, just a fancy version of degrees, if I begin to increase the value within this argument, this math cosine function is always going to return a value -1 to 1, and it's just going to pulse between -1 to 1 over time, and if we're continuously adding on -1 to 1 to our original position, we're going to get a movement effect on the x-axis for whatever vertice we're looping over. So if we want to change the value of this over time, we're going to go outside of our animate loop and create a let called frame. This is going to be equal to 0 to start, and then for every frame we actually loop through, we're going to be adding a small number onto frame over time. This is going to represent what frame we're on, how many times we've called this animate function. And now that this is increasing for each time we loop through animate, we can put it within our math cosine function. So we're going to put frame here. So if we add frame on in there, we're not going to see anything just yet. We can always test if this is working by only looking for the first iteration of this loop so we don't bug out the console. What we can say is if I is equal to 0, meaning it's the first iteration of this loop, let's go ahead and console log out math cosine frame to make sure that this is actually increasing and decreasing as we want to. You'll see it's going down, down, down till we hit -1, perfect, and then eventually it's going to go back up until we hit 1. So we know that's working, and we know that array should be affected. We can also console log this out to make sure that's working as well. Array I. And indeed, that value is changing for the vertice we're looping over. So why isn't it actually being affected right here? Well, the reason is when we are updating our position right here and we're animating it, we need to make sure that we're telling our attribute that it needs an update. So if we set this equal to true, we save, you're going to see that it just immediately moves off the screen. And eventually, it's going to come back. So we do have the pulse effect for each individual vertice, but they're all moving at the exact same time so that they go way off the screen and eventually they pulse back to the left side of the screen. So if this is happening, what you can do is you can set math cosine to be something a lot smaller. To make it a lot smaller, you can multiply it by a value 0 to 1. We're going to multiply it by something like 0.01. You're going to notice that the x value is moving left and right, but this isn't really the effect we want. We want each individual vertice to be moving in a random position independent from one another. So rather than each vertice have the same value produced by math cosine frame, we need to add some random value inside of this for each individual vertice. So where we are looping through our position right here, we can do all the work to add in a random position for each vertice as well. Right now we are looping through every 3 iterations, and each 3 iterations are going to have their own random value, but to access these random values in kind of like a buffer format where everything's stored in an array, well, we're going to want to create an array called random values. This is going to be equal to an empty array to start. And as we're looping through each vertice in this random values array, we're going to push in a new math.random value. So at the end of this, after we go through the whole for loop, if we console log out random values, we should see a list of random values. And to clean this up, let's go ahead and get rid of any additional console logs, make sure we're only looking at exactly what we need. I'm just going to Command F to make sure we're only logging out those random values. It looks like I got everything, deleted them. And these are all the random values. We have an array of 676, which should be how many vertices there are within this default plane. So now that we have this random values array, let's go ahead and attach it to our plane mesh position attribute, similar like we did right here with the original positioning. I'm going to reference random values onto this, set it equal to our random values array. So now when I console log out our positions attribute, console log plane mesh geometry attributes position, we should see those random values being stored in here, and there they are. You'll see we have a vertice count of 676. We also have 676 randomized values that we can now use to make sure that these are moving at different rates compared to before. So now that we have these random positions, we can begin to insert them within our math.cosine function here. So what I'm going to do is onto frame, I'm going to add on our random values array. And if we just want to reference random values exactly like this, we need to make sure we're pulling it in from our position attribute. So here where we are destructuring stuff, I'm going to make sure that I'm pulling in random values. And we can't add on an array to a frame. We need to make sure we are accessing the random value within the array we are looping through. So to get that, simple enough, all we need to do is reference I. If we console log this out and look inside of our buffer attribute, you're going to see now we have this array full of random values. But there is one issue here. The array we're looping through to change all the positions is this array, which consists of 2028 values. We need to make sure that this random values array is equal to that, or else we're not going to have a randomized position for both x, y, and z. We're only going to have them for x. So what we can do is, within our for loop where we are populating this random values array, is we know we need 3 times as many random values. The reason we're not getting 3 times as many random values right now is because we're skipping over every 3 values within this loop. So what I'm going to do is I'm going to change I plus back to I plus plus, which means we're adding 1 onto I. We're looping through every value within array.length rather than every 3 values. But we know this code right here is dependent on looping through every 3 values. So if I want to make sure, even though this for loop is looping through every value, if I only want to activate this code for every 3 values, I can use a modulus operator. So I'm going to say if I divided by 3 has a remainder equal to 0, then I want to run this code. This is going to give us the same effect for everything we have right here. But at the same time, we're going to be able to push in a random value for every iteration of this loop. So basically we only have to call this for loop once, but we still get the best of both worlds because we can call this code and we can also call this code. So go ahead and save this and then look within our array again. And now random values does indeed have 2028 values, and our array positioning is still altered correctly because we're only calling this code for every 3 items within our position array. So that's looking good, but let's go ahead and start animating these correctly with our randomized value. So if I go ahead and scroll on down, we want to make sure that each vertice has a different value outputted by math.cosine. So we have frame, which means everything is going to be the same, but we want to add on that random value. So we need to access our random values array. And if we want to access this directly, we need to make sure we are destructuring from our position attributes object. So we'll make sure we add it in right here. And you can't add an array onto a frame. We need to make sure we are selecting the exact value we want to add onto this. So I'm going to put I right here, which is going to select the value we are iterating through. We'll put I there. And now you'll see the X values are much more randomized. Everything's not just pulsing back and forth, but they have their own little direction in place. So this looks like a lot of movement. I'm going to slow this down even further by multiplying this by a lower number. And even that might be a little too low, so I'll increase that a little bit. And just go to taste to something you like. I think for how big our plane is, I think 0.003 is going to do. But let's go ahead and make sure that this is also randomized in the Y direction. So a simple thing I can do is I can just copy this line of code that we just created. Above it, I'm going to comment Y. This is the Y coordinate that we're going to be altering. And to select the Y coordinate within our buffer array, I'm going to add 1 onto I. That is going to be where the Y coordinate is. I'm going to do the same thing for the original position because we want to make sure we're grabbing that initial value and then setting the new value equal to that. And then we're going to be calling math.sine instead of math.cosine. Cosine and sine work together to create full circular motion. So if we add sine onto this instead of cosine, we're going to get a much more randomized effect compared to if we were just using cosine for both. So if we change cosine to sine here, and then make sure we are referencing not just I, but the second value within our randomized array, we're going to get something that looks even more randomized. And you'll see now the Y coordinate is randomized as well. But there's still one little thing here, and it kind of looks like all of our vertices are moving in a circular motion in the same direction. If we want to randomize this even further, remember the trick I told you about getting a negative value with math.random as well? Well, when we're pushing in values into our random values array, what we can do is subtract 0.5 from math.random to make sure that things are going to be in a different direction. So I save this. So now you'll see we have a lot more randomized movement in the Y direction. So this is definitely something you can keep. If you want to get closer to the original like we have over here, you're going to want to copy these attributes. And I know I said I wouldn't come back to these, but just for the sake of completing this as close to what we have over here, let's go ahead and change these values to match up with what we have in the original piece. So we know our width right now is 24. We can change those at the top where we have our data object for GUI. We're going to change our width equal to 400, which is what it was in the example piece. Same for height. That is also going to be 400. Go back to the example, reference what we have. Width segments is going to be 50. Height segments is going to be 50. Change 25 right here to 50. Let's see what we get. Well, now we are just way too zoomed in. An easy way to fix this is to find your camera Z position and set it to whatever you would like to make sure that it's further away from your plane. I'm going to set it equal to 50. That's definitely going to pull it away a lot further. But now we don't have as much depth as we did before with this larger plane. So we want to go to where we are randomizing our vertice position. And you can see right here, this is where z is randomized. Well, right now they're only being randomized where the z vertices come closer to us. Remember, if we subtract 0.5 from math.random, well, now they can go further out or closer to us because we're getting any value negative 0.5 to 0.5. But there's still not a lot of depth. So if you want more depth in either direction, we can just multiply this by a larger number. And now we do indeed have a lot more depth. So we're looking pretty similar to the example piece over here, but you'll notice the example piece is a little darker. If we want to make this a little darker, well, it's going to be based on our light positioning. Over here, the light positioning is closer to us and above the plane. But if we look over here and we look at our light positioning, well, we're just setting it further to us and looking directly at the plane, but there's not really any angle in the y or x axis. If we want to make sure that it's shooting at an angle, we're going to get more shadows, which gives it more depth. So what we can do is we can set its y position equal to 1, which means we're going to be moving it upwards at a 45-degree angle rather than just facing the plane directly. If we save that, well, now we have that depth we're looking for. It looks very similar to what we have over here. Maybe it's just in a different direction. That takes care of the color, but there's still something just a little off. If we want to tailor this even further, let's go back to where we are randomizing our vertice position. And our x and our y's are kind of lining up with each other right now. If I go across this, you'll see all of our vertices are almost creating a straight line, almost. And over here, they are just much more differentiated from each other. So if we want to differentiate the x and the y a little more to create less of a more straight edge effect, what we can do is we can alter the set y position to be a little larger than it was before. So we're going to multiply our y by 3. We're also going to multiply the x for our vertices by 3 as well, randomize it a little bit more. And now that is pretty one-to-one what we have over here, maybe just a different direction, but you still get the same exact effect that we have in the example piece. Play around with these a little bit to really get different effects, and you can see just how much it really changes the landscape you're working with. I'm going to stick with these variables, and then I'm just going to make sure that our dat.gui is fixed. So instead of limiting width to 50, I'm going to make sure that this can go all the way up to 500, and then I'm going to make sure our segments can go up to 100. And now we have the ability to alter this, but we're almost done with this plane thing completely. If I go ahead and alter this just a little bit, you're going to notice that our polygons are a little messed up, and we also get an error in the browser. This is due to the fact that things such as our random values and things such as our original position are only being created on load. We need to make sure that these are also being created whenever we change one of the sliders up here. So what I'm going to do is, where we are randomizing our position, I'm going to go ahead and take all of this code, go up to our generate plane function. I'm going to paste it in. We have duplicate code right here, which is our old randomization code. We can go ahead and get rid of that. If we save, we're not going to get anything right here because we're not calling this randomization code things that stores properties onto our position attribute array like we need it to. So what we need to do is we need to make sure that we call this generate plane function after we actually create our mesh. And you look inside of this function, we have all of our color setting done right here. Scroll a little further down, we have the exact same code right here. We can just go ahead and get rid of that because we're going to be calling it again using the generate plane function. So after we create our mesh, we're going to generate a plane which has all the randomization in it, and we still get the same effect, but now once we go ahead and change the value of height and width, things are randomized as before. Our hover effect still works and our colors are still taking place. Change pretty much any value here to get the exact effect we want without anything breaking in the process. And one more thing to touch this up, I promise this is the last thing. If you notice you're getting too much of a circular movement here, what you can do is where you are populating your random values for this array, we're just going to look for random values. This seems to be where we are populating things. We're only pushing through any number 0 to 1 within this random values array. But math, sine, and cosine, if we want to extend the full random range of -1 to 1, we need to make sure that we're supplying cosine or sine with a value of 6.28 pi times 2. So really, instead of just any value 0 to 1, we want to make sure that we're supplying math random times math pi times 2, which is going to give us 6.28. We're going to be getting any number 0 to 6.28 instead within this random value array. Just make sure that you multiply that value right there or else things will break. And now that is going to be a lot more randomized compared to what we have before. You can even test this if we can't really see your movement too much. You can either zoom in Or you can go back to your animation loop, increase this factor right here by something larger, such as 0.1, and you should be able to see your animation a bit better. Do the same thing for Y. And now we're going to have true randomization for each vertice compared to what we would have had beforehand, where everything is just limited from 0 to 1. Okay, so finally, looking at our to-dos, we added in vertice movement. All we have to do now is add in HTML and integrate with JavaScript. This is the easiest part in my opinion. Apologies if this is a little hard to grasp, guys. It's a little hard for me to teach, to be honest. So to add in HTML, let's reference our beginning piece. We're going to go ahead and see that we have our name, we have this little headline, and then we have a button which is going to go to some other page on your website. So to add in HTML to this, we're going to go on over to index.html, and here we're going to start adding our markup. So you can do this within this default ID app, or you can do it without it. It doesn't really matter. We're going to go ahead and write our markup inside of this. What is our markup look like right now? Well, we have this one container that consists of, it looks like a headline, another headline, and a button. So let's go ahead and make another container. It's going to be a simple div. And then we have this main headline for our name. The first headline, in my opinion, should always be H1, even though it's smaller. So I'm going to go ahead and make this an H1 tag. And then pretty much anything under a headline, I by default make a paragraph tag. And then I need to make sure that I add a button to this as well. So I'm going to add this button markup. It's going to be called view work. And remember, this is the finished product. We need to make sure we're going back to the one we're working on. If we look at our HTML, this is what it's going to look like by default. We need to make sure that we alter it to look something like this and that we can still interact with our background in the process. So to start styling this with CSS, the first thing we want to do is get this one div. If we inspect this div by clicking on this button in the console, inspect the div, we need to make sure we get this div laid on top of our canvas piece, or Three.js piece. How do we do that? Well, if we want to take it out of the document flow, meaning we can overlay it on top of other things, we can give it a style of absolute. So what I'm going to do is within these style tags right here, I'm going to add an additional style called simply .absolute. And this is going to have a position of absolute. So now if I add this class to our div right here, it's going to take the style of position absolute. I'm going to add that on. And once we add on position absolute, you'll see it's taken out of the document flow and it's overlaid on top of things. Next up, let's change the color of the text so it's white and it contrasts a little better than what we see right now. So to make sure our text is white, I'm going to create a class called text white. This is going to have a color of white. So now I can pretty much just add this to our default div, and all the stuff inside of it, minus our button, is going to have the text of white. So text white, save. And now our text is white, which is perfect. So you'll notice the way I'm writing CSS, I'm writing these using utility classes. Basically, each class gets one style associated with it. And the reason for this is it just makes your HTML super easy to write. Rather than thinking of a name for a class, such as container wrapper or something along the lines of that, you don't have to think of a name because all of these names I'm coming up with represent exactly the style that is inside of them. At the same time, these are all standardized using a framework called Tailor and CSS. Basically what I'm doing here is I'm replicating the style of Tailor and CSS, but eventually you're going to get to the point where writing all of these classes is super cumbersome and tiring. So rather than write all of these manually, what we can do is we can go ahead and visit tailorandcss.com, search for get started, click on read the docs, and we're going to do a command F for CDN. Tailor and CSS doesn't recommend you use a CDN, just pulling in the framework using a link because there's a lot more customization available using their other installation method, but for our purpose of just getting this inner project and using it, this is totally viable. So what I'm going to do is I'm going to paste this link right above our style tag, and just like that, we now imported Tailor and CSS into our project, and we can use all of the styles associated with Tailor and CSS, including things like absolute and text white. We can get rid of these two classes right here, save, and now you'll see that our text is still taking on the styles of absolute and text white, with a few things even different because Tailor and CSS has a reset associated with it. It sets some default browser styles equal to their bare bones equivalent. So adding Tailor and CSS is pretty good in my opinion for giving you a full CSS reset while allowing you to use all the nice classes within the library. So I'm going to walk you through how to style this exactly with Tailor and CSS. So we know, looking at our example over here, our text is centered. So Tailor and CSS has a class of text center. What does this do? Well, it centers your text. Easy enough. If you're ever unsure of what class you should be using within Tailor and CSS, you can go on over to their docs, search for anything such as align, text, align, and you're going to see the exact classes you can use. So we just went ahead and used text center, and now our text is centered. But next up, we want to make sure that this text, the whole container, is actually centered directly in the middle of our screen. So we're going to do this using position absolute. This is a little trick from the old days, but it's still relevant today. We want to make sure that within our div right here that we add a style of top. This is going to push the container down from the top of our page down 50% of our browser width, well, the container width. So it's down 50%, but you'll notice it's not exactly centered. If you want to exactly center this, you can add a style of transform, translate, y, -50%. And now this is going to be centered vertically perfect in the center. So we want to take these two styles that we just wrote in line within the browser and make sure that they're within our code so that they take effect permanently. So I'm going to add in a style tag, and I'm just going to add in two inline styles here. There's nothing wrong with using an inline style. Don't let anyone tell you otherwise. If you need to get some quick style code in there that's not in Tailor CSS, this is how you're going to want to add in a style. You don't need to write a separate class or anything. In my opinion, it's just extra work. So if we add in the style right here, you'll see that now on refresh, everything is centered vertically. Perfect. But how do we center things horizontally? Well, if we set our left attribute equal to 50%, it's going to do the same thing. It's going to push it over 50% from the left-hand side, but we need to make sure that the center is within the center of our screen. So what we can do is, instead of translate y, we can just use translate, which takes an x value for its first argument. So x is going to be pushed to the left by -50%, and then the y value for its second argument. So we're going to push it back up by -50%. And now this is centered perfectly in the middle of our screen. And the cool thing is, if we inspect our div, it's only taking up the exact width of our content. So our hover effects are still going to work as we move our mouse around our actual object there. So starting to look pretty good, but if we look over at the piece, we have fonts that just look way better. Picking out the right font takes a little bit of experience in my opinion, but let's go ahead and use the two fonts that we already have in place. If I go ahead and inspect this piece, we can see what fonts those are, and you'll see that this is actually a font of XO2. So this is a Google font. If we want to add a Google font onto our page, we're going to go ahead and search Google Fonts. We're going to go to the Google Fonts website, and then we're going to search for that font exactly. So XO2, this is the font I was using, and I was using the italic variant. I'm pretty sure I was using regular. So if we want to select this font, I'm going to go ahead and select this style, and you'll see that it gives you a link in which you can use to import it into your project. So right above our Tailwind link, I'm going to paste in that Google Fonts link. And it gives you a little bit of code on how to use this within your project. If you'd like to use this within your project, well, you have to set your element to have a font family of XO2 sans serif. So Tailwind doesn't know we want to use this font. As a result, we're going to have to create our own font class. And the name of this font is XO. So I'm going to create a class called font XO and set it equal to font family XO2. So going back to our app. Now, if we assign our paragraph tag to have a font of XO, now we are using the same exact font we got from Google Fonts because we are pulling it through Google using a link tag, and then we are setting this font XO class equal to XO2, and then finally using it, setting our paragraph class equal to that font. So off to a good start. Looking back over here, you'll see up here we have some sort of monospace font where each character is the same length as the next one. It gives for a very techie feel because if you look at our text editor over here, this is using a monospace font as well. You don't want some sort of font that has different widths for your text editor because you want to make sure that you have some sort of standard in place for when you look at your code, everything is in the same spot, not based on some specific character width. So this is a monospace font. Let's go ahead and use a new Google font to get this in. We're going to go back over to Google Fonts. I'm going to exit out of this. I'm going to scroll up to the top, go back to the home page, and I'm going to search for mono. So a mono font that I really like actually is going to be the Space Mono font. It's something I've used on another project and I like it a lot. So I'm going to go ahead and select this. This is just going to be a regular version of it. So I'm going to select the style. If you don't see the little pop out on the right like before, you're going to want to scroll on to the top. Make sure you click this. And now we have two font families selected, XO2 and Space Mono. It's going to generate a new link for us that pulls in both of these at the same time. So what we can do is, back at our previous link, we can delete these two that were supplied to us by Google prior and paste in the new one. So now we have access to two fonts rather than one. And the nice thing about Google Fonts is it tells you how to use them. So we're going to create a new font called space mono, and this is going to be equal to font family space mono. Makes sense. So now that we have this font pulled in, we can set our h1 equal to font space mono, go back to our app, and now we have that mono font in place. So now we just have to set these fonts to the correct height, the correct font weights, and so forth to really get these looking good. So whenever you want some sort of subheadline, such as your name, and this should be the main focus, you want to make sure that subheadline is de-emphasized. A great way to de-emphasize text is to make it smaller. We can give this a class of text SM. That is going to be 14 pixels. You'll see that smaller, it's a little bit de-emphasized compared to this. Another way to de-emphasize text is to make the other text larger. So if we want to make this text larger, we're going to select our P tag right here and give it a size of text XL. So that's a little bigger. We can go ahead and make this even bigger by adding in a 2XL. And I think I like where that is at. So our text is de-emphasized at the top. This is obviously our focus. And you can keep this as is, that's totally fine. But something I like doing for my subheadlines is I like making them uppercase. I just feel like it looks a little better. So for my subheadline, I'm going to give this a class of uppercase. And whenever you have subheadline uppercase text, it's always good to give it letter spacing. Make sure that each character has breathing room from the one prior or after it. So what I'm going to do is add in a tracking wide class, which is going to increase the letter spacing between these letters. You'll see it increase very slightly, and this is something I really like. I'm definitely going to be keeping this. So I do want to differentiate this text down here a little more from the subheadline. So what I'm going to do is I'm going to go back to Google Fonts, and for XO2, right now we're using regular 400 italic. I want to make sure that I'm using the bold version of this instead. So I'm going to scroll down to the bold italic version, which is this right here. Need to exit out of this. Select the style, scroll up to the top. You'll see that this is where the regular 400 italic is. We can just go ahead and remove this because I don't want to use it anymore. So now we're pulling in the bold version of this font. How do we use the bold version of this font? Well, we simply pull in this new Google Fonts link, go back to our app, and now we're pulling in that bold version. So it's differentiating our text a little more from the text up here. Now, something about this just looks a little sloppy. And the reason it looks a little sloppy is because this text isn't anti-aliased. Anti-aliased means that the browser is going to apply some effects to make sure that the edges of your text are as crystal clear as possible. And you can see this in action. If I go to my body tag and just start typing in anti-aliased, we're going to get this style right here, WebKit font smoothing anti-aliased. You're going to see we get this bold, chunky, a little dirty text, but once I add it in, things are a lot more clear than they were before. So whenever you have any project, you want to make sure that you're adding the style to your body to make sure that all your text is as crystal clear as possible. So I'm going to go ahead and add that in there. Set this equal to anti-aliased, like so. And now that's going to take effect by default. So if we go ahead and compare our piece to the one over here, we're looking pretty similar. Let's go ahead and full screen it so we get the full view of things. Looking pretty similar. The only difference right now is our text is a little smaller compared to what we have right here. So that's something we can do is we can go ahead and increase the size of the text a little more. This is going to be text 3XL. Go ahead and compare that. Maybe we want to go one size higher, text 4XL. So if we go and check our example piece, go back and forth, this looks pretty close. It's not exact, but at the same time, our new one is looking just as good. All we really need to do now is style our button to look something like this. So let's go ahead and do that. On top of our button, we want to add a class. We're going to add in a border to our button using Tailwind. You'll see it automatically adds in a white border. How nice is that? Let's go ahead and give it some padding. If we select our x-axis padding and add in 1 rem of padding by using px4, you'll see it's going to expand it by a little bit. Let's go ahead and do the same thing for the top. Typically within a button, you want less padding on the top and bottom side than you would on the left and right side. So our vertical axis padding is going to be a little less, and that's looking pretty good as well. Let's round the edges of this button by using rounded, large, and then this button text just looks way too big for me. So what I'm going to do is I'm going to shrink it down to text SM. And to keep the font styles consistent, I can change the text of this to match my subheadline up here. So all I need to do that is select font space mono and add it on to our view work button. And remember, every time you have a monospace font, if you're using it as some sort of label or button, it's usually better to make it uppercase. Just looks a little better in my opinion. And that is looking pretty techy. Looks very professional, something I like. The button is obviously too close to our headline up there. So what I'm going to do is add a margin top of 4. That's going to push it. We can push it up even further by adding on 8. And that looks pretty good. Maybe I'll even go to 12, just give it a little more breathing room. I think I did like it with 8 a little more. It's just kind of like a taste thing at that point. And this looks really cool, but right now we don't have a hover effect, so the user may not know that this is actually a button. So to add a hover effect, I'm going to use a Tailwind prefix called hover. This is a really nice way to add hover effects and stuff is you can just type in hover behind any class that you want to use within Tailwind, and whenever you hover over it, that new class is going to take effect. So let's see. When we hover over this, what class do we want our button to be? Well, we want to give it a background of white. So we can just select the background white class from Tailwind, and now when we hover over this, the background is white, but now we can't see our text. So we'll add in another hover class. What color do we want our text to be on hover? Well, let's say text gray 800. So now when we hover over it, our text color changes and we can actually see it. And it's even cooler with our little background effect on the actual Three.js piece because it lights up the button in the background as we hover over it because it always follows us at all times. So the very last thing I'm going to show you is how to link this button to another website. To make this button link to another website, we're actually going to change the button to an anchor tag. By changing button to A, we're going to give it an href attribute which specifies where do we want to link to. Well, if I want to link this to, let's just say chriscourses.com, I can just go ahead and grab this URL, plug it within my href code, and now when I go back to my app, you're going to see, one, the styling's messed up, but now when I click on this, it goes to chriscourses.com. Why is the styling messed up? Well, the styling is messed up because by default, anchor tags have a class of inline, which means things like margin start messing up along the way. Our margin isn't taking effect because it has the class of inline by default. So instead, what we can do is we can assign it a class of inline block. And just by assigning an inline block, it's going to make sure that the margin takes effect and that it is positioned correctly. So now when I click view work, it goes to my new website or whatever page you would like to use, but we still have all the effects of being able to move this background. We can even zoom in and out if we would like because we have the OrbitControls still on it. We just have this really nice background effect compared to what we would have otherwise with just having text on there. This creates for something that really wows your visitor as they come and visit your website. So I know this is a long tutorial, but hopefully you guys learned a ton in the process. If you would like to learn more about how to extend this even further, such as adding in browser responsiveness so that your canvas expands the full width of the browser, and in addition, something else I'm going to be teaching is how to create this transition effect that turns the camera and bolts it into an array of stars. If you would like to learn how to turn this piece right here into that, then be sure to head on over to the premium course in the description of this video. I'm going to be supplying the first lesson for free. Otherwise, I hope you guys learned a lot, and I'll be sure to see you in the next video. Peace.